Chapter 1 Preface. This book has grown to its present state of publication during more than 3 years of wartime. Glanced at superficially, its outlines may appear to comprise a well-defined entity. However, those who have contributed to its growth are aware of many a wound inflicted upon its form by the war and of many a defect, the scars of which are conspicuous enough, though they have not abolished the integrity of the basic idea. The subject of the book is physiology, not physiology from above. But physiology from below, not physiology originated essentially to fill human needs and help suffering individuals. But physiology as a branch of physical chemical science dealing with life as a physical, though exceedingly complex system that may be subjected to scientific analysis like any other natural object. In this preface, the idea of the book will be made clear to the reader by a brief abstract from the 8 sections, which appear in the table of contents. It will be convincingly shown that it is not only possible, but of importance, to anchor physiology even deeper in physical chemistry than was done previously. That is, even closer to the fundamentals on which our concepts of inorganic nature are erected. And when one tries to segregate the elementary processes combined in the life of a cell and to analyze them with the new tools of modern physics, this attitude makes more discernible the great number of unsolved problems. During the last 4 decades, a tremendous revolution in our conception of the inorganic world has taken place, which during the last 20 years has progressively seized the aspect of the world of organisms. For qualities of matter, spatially distributed quantities have been substituted. Chemistry has more and more become a branch of physics. In our book, this trend is described in sections 1 and 2. Beginning with a survey over the fundamentals of classical physical chemistry, a comprehensive part is devoted to outlining the numerous grades of structural complexity, beginning at the low level of atoms and molecules and defining the various electronic and nuclear forces which are involved in their linkage or disruption, then ascending through levels of greater and greater aggregation. The rank of such giant molecules is attained as we meet in the synthetic polymerization products of organic chemistry on the one hand, and in the huge aggregates of amorphous colloidal micelle of anisodiametric thread-like and leaf-like units, from which by interaction and orientation emerge the fibrils and fibers, the films, membranes, and septa, so widespread in living cells, with the subsequent sections 3 to 8. The actual field of cell physiology is entered. Section 3 briefly refers to the structure of protoplasm. Here, reasons are offered for the existence of submicroscopic particles of an even higher order of aggregation, as these particles are intermixed with macromolecules and molecules of smaller and smallest dimensions inside and around the protoplasm. It is made clear that they are subjected to spatial and temporal changes brought about especially by the metabolic reactions. Therefore, the next logical step is to assign functional significance to the various structures and to their changes. Among these superstructures, the most outstanding importance is claimed for the plasma membrane as an interface between living and non-living, sections 4 and 5. The plasma membrane has often been thought a mixed film, and it will be shown that on the basis of studies upon red blood corpuscles, plant cells, and other objects, various fairly simplified patterns could be proposed to portray its submicroscopic architecture. Also changes of permeability due to disarrangements in this interfacial colloidal structure in response to the effluences of ions, narcotics, the electric current, and others. However, it also will be explained in these sections that these patterns are found entirely unsatisfactory in view of the fact that permeability is altered not merely following artificial alterations in the surrounding media or following external stimulation. Instead, this mixed film appears as an active organ where metabolic processes are somewhat associated with a transport of solutes, or of solvent against zinc concentration, gradients between the interior of the cell and outside. In other words, work derived from the expenditure of metabolic energy can be done by this superstructure, provided the free energy is disposed of in an adequate succession and characteristic involvement of the chemical reactions. As explained in sections 6 to 8, problems of general cellular physiology, namely the mechanisms by which in such submicroscopic cellular structures the liberated energy can be utilized to perform work. Beside the plasma membrane, there is another microstructure, the thread-like aggregates of mollusks and molecules in muscle, where the problem of interrelation between mechanism and metabolism seems to be more accessible. It will be shown, section 7, that the myosin threads themselves seem to release the transformation of certain muscle metabolites, which reciprocally cause the threads to shorten and to relax. Possibly, one likewise can arrive at an approximate interpretation of the mechanism of active transfer. This characteristic property of the numerous absorbing and secreting membranes by comparing them with the sieve membranes as analogous, which endowed with pore scuff different widths, with pore walls carrying different electric charges, and placed in solutions of different ion concentrations, may be assumed to establish anti-diffusion and anti-osmotic effects with water and ions, section 8. Certainly such interpretations lie, as yet, rather far beyond the limits of exact and definite statements. However, perhaps the viewpoint of the physicist, which in this book has been pushed into the foreground, lends itself to such extrapolations, especially as physics is on the way to open new and wide areas to problems in the field of molecular structure. On the other hand, in choosing a new start from a new baseline, we have ignored or at least neglected in our text several important recent trends of physicochemical investigation into physiology, and also older observations and conclusions, which in the meantime have been turned over into the stock of common knowledge. In this respect, the book cannot claim to offer a universal information in the field of physical chemistry of cells and tissue, but it may guide to new roads into the unknown. Grateful acknowledgement is made to the Z. Carnegie Corporation of New York for a grant and aid to complete and to edit this book. Special thanks are due to the Blakiston Company for their liberal agreement to extend considerably, with respect of wartime conditions, the time limit of the contract, and for their unfailing cooperation and assistance. Chapter 2, Section 1, Selected Principles of Physical Chemistry. The recognition of physicochemistry as a separate branch of science is associated with the foundation in 1887 of the Zeitschrift Physikalische Chemie. The early volumes of this journal contain the well-known papers of Arrhenius, Van Hoff, Oswald, and Nernst on electrolytic dissociation, osmotic pressure, dissociation constants, and electromotive force. These papers have been preceded, however, by a number of important contributions, including the work of Poiseuille, 1843, on viscosity, Wilhelmy, 1850, on reaction velocity, Fick, 1855, on diffusion, Goldberg and Waage, 1864-67, on mass action, and Gibbs, 1875-78, on heterogeneous equilibrium. A number of the early workers in physical chemistry were men of biological training. Poiseuille was a physician, Fick was a physiologist, and the work of the botanist Pfeffer, osmotic pressure, 1877, and de Vries, plasmolysis, 1882, as well as that of a physiologist. Hamburger, hemolysis, 1883, was used by Van Hoff in the development of his theory of solutions. In more recent years, the application of physical chemistry to biological phenomena was particularly emphasized in the writings of Höber and of Baylis. Physical chemistry has been divided into the study of laws applicable to systems in equilibrium and of laws governing the rates by which equilibrium is attained. Since living cells and tissues are not in equilibrium, although many of their properties show remarkably steady states, the discussion of rates must occupy a prominent place in the present work. The treatment of physico-chemical principles in the first part of this book is based on the assumption that its readers already have some knowledge of the subject. The study of this book might well be preceded by the reading of one of the elementary texts in the following list, or accompanied by the use of one of the intermediate or advanced texts. 1. Pick's Law of Diffusion. Perhaps the simplest kind of physicochemical reaction is one which is hardly chemical at all, namely the diffusion or spontaneous transfer of a dissolved substance from one part of a solution to another. It was shown by Thomas Graham as early as 1850 that the rate of diffusion varies with the nature of the dissolved substance, and the quantitative description of the diffusion process dates from 1855. The year of the publication of Pick's law. Pick made the reasonable assumption that the flow of matter in diffusion ought to follow the same law as the conduction of heat, which had been treated mathematically by Poirier, with the substitution of quantity of solute for quantity of heat and of concentration of solute for temperature. That is, the rate of diffusion, or the amount of substance crossing a given area in an infinitesimally short interval of time, ought to be proportional to the cross-sectional area and to the concentration gradient. In symbols, here dN is the amount of substance which passes in the time dt across an area where the concentration gradient is dc dx. The constant of proportionality, or the diffusion coefficient of the substance, is represented by z. And the negative sign appears because diffusion takes place from a region of higher concentration to one of lower, Pig 1. Pick realized that the value of xi for a given solute and solvent tended to increase somewhat with temperature, and later work has shown that d also tends to increase toward a limiting value as the solution is diluted. The latter trend is especially characteristic of solutions of electrolytes. Because of these minor variations, it is preferable to refer to d as the diffusion coefficient rather than as the diffusion constant. It will be seen from equation 1 that d has the dimensions of area divided by time. In the centimeter gram second system, 1 is expressed in centimeters second, but it is sometimes expressed in square centimeters per day. If dN is expressed in moles and dx in centimeter, dc must be moles per cc, not moles per liter. If the minor variations in d are neglected and the area is fixed, equation 1 still contains 4 variables. This number may be reduced to 3 by a consideration of the relation between n and c in an element of volume bounded by parallel planes of area, A separated by the distance dx, figure 1. The concentration will be changing in the time dt. The number of moles of substance which enters the element of volume between these planes must differ from the number which leaves it, because the concentration gradients at the two planes are not the same. If dn moles enter in the time dt, the amount of substance which accumulates is divided by the volume at x, gives the change in concentration in the time rate of change in concentration is therefore. The last factor may be evaluated by a differentiation of equation 1. Keeping the time constant, multiplication of these two equations yields the second form of Fick's law, which is equation 2 is the most general equation for Diffeslon in one dimension. It represents a special case of the still more general equation for 3 dimen before equation 2 can be used. It must be integrated or solved. Such an equation has many different solutions, and the one which is to be applied in any case must be determined by the boundary conditions characteristic of the experiment. For the diffusion of a solute in a vessel of uniform cross-section from an infinitely long column of solution into a similar column of solvent, Stefani obtained a solution of equation 2, which is given by here, C initial concentration of solute in the lower layer, and C is the concentration at time t and distance x from the initial boundary. The sign of x is positive if it is measured upward into the original solvent layer. Equation 3 applies to experiments with finite or even short columns if the time is short enough so that there is practically no change due to diffusion at the bottom and the top of the tube. The function is a probability integral whose values are to be found in mathematical tables. The values of this integral lie between 0 and 1, passing from 0 to 0.9953 as y from 0 to 2. In using equation 3 for the determination of d, a value of the integral is obtained by substituting numerical values of c and co. The table is used backward to get y. And finally, d is obtained from the definition of y and the measured values of x and t. The nature of the variation of c with xy, as given by equation 3, is shown in figure 2 at the level of the initial boundary y0x0. The equation indicates that C will have the value CO2 at all times after diffusion has started. If the initial volumes of solution and solvent are equal, Q will also be the final concentration at any level. In a somewhat different type of experiment, the concentration of the initial layer of solution is maintained at the value CO throughout the time of diffusion. For this case, the solution of equation 2 is, with the same notation as in equation 3, equation 3I was found to apply to diffusion from a solution kept saturated by the presence of solid salt, as well as to diffusion from a large volume of solution, not necessarily saturated, into a tube full of jelly containing the solvent. In such cases, the final concentration in the solvent layer will be CO. And the relation of C to X is exactly like that shown in the lower half of figure 2, if the ordinate of the horizontal line KL is taken as CO2. Equations 3 and 3A yield an important and simple relation which is characteristic of diffusion processes. If C is constant, Y must also be constant, and the definition of Y indicates that under these conditions, X is proportional to each T. That is, the distance traveled by a layer of any given concentration should vary directly as the square root of the time of diffusion. This relationship has often been verified. The experimental method is particularly simple when the diffusion takes place in a jelly containing an indicator substance. 2. Measurement of diffusion coefficients. The classical method for the determination of diffusion coefficients involved extremely painstaking experimental work and the creation of special mathematical tables. The solute was allowed to diffuse upward from a layer of solution in the bottom of a uniform cylindrical vessel into a layer of pure solvent, usually 3 times as thick as the initial layer of solution. At the end of the allotted time, the mixture was separated with as little disturbance as possible into 4 equal layers, and the concentration in each layer was determined. Method Rudolf, whose results occupy a prominent place in tables of diffusion coefficients, and Cohen and Bruins, who described refinements of technique which yielded values accurate to 0.3%. An elaborate refractometric method for the determination of the diffusion constants of proteins was developed in S. Edberg's laboratory by Lamb and Poisson. Diffusion coefficients are most simply measured by the porous diaphragm method of Northrop. And Anson, their improved APGRSs, is shown in 1. L's with fritted discs of Pyrex glass are listed in the catalog of the Umming Glass Works, Corning. NY1 on the specific gravity of the solution must be appreciably higher than that of the solvent. The difference due to 1% of dissolved protein is sufficient. It is necessary to avoid all stirring, even of the water in the bath by which the temperature is controlled, because of the disturbing effect of vibrations. J.H. Northrop, 1941. Work. Northrop and Anson used 0.1 AHTL as standard, accepting a value of Ohm, which they later concluded to be in error. More recently, they recommended 2 NaTL. This substance was preferred because its diffusion coefficient does not vary appreciably with concentration. The method is characterized not only by similicity of technique, but also by the ease with which the diffusion coefficients are calculated. If the amount of substance which has diffused is so small that the initial concentration may be considered to be unchanged, while the lower liquid may be considered to be pure solvent, then the constant concentration gradient is simply CFXE, where X is the unknown length of the path of diffusion in the pores of the membrane. The analysis of the lower liquid gives the value of Na, which replaces dNdt in the first form of Pick's law, if the rate is constant. The diffusion coefficient is then given by if it represents the effective but unknown cross-sectional area of the pores of the membrane. The ratio XA, or the cell constant for the membrane, is obtained from the calibration data. And even if C is known only in terms of some arbitrary unit of biological activity per cc, the value of D will have the correct dimensions if it is expressed in comparable units. Northrop and Anson considered this simple calculation to be adequate if the amount of substance which diffused through the membrane during an experiment was not more than a few % of the total amount present. but they used for the calculation a mean value of C, for example, C equals 0.98 Co if n equals 4% of the total solute. The membrane method is not limited to those diffusion experiments in which the initial concentration changes but little. After the diffusion gradient was established by a preliminary run of a few hours, McBain and Liu replaced the lower solution by fresh solvent and started the experiment proper with the upper solution at an unknown initial concentration, Co. The value of TO could be determined from the volumes of the two compartments and the analysis of both solutions at the end of the experiment. For such an experiment, Pick's law may be written where Ci and C2 are the concentrations of the upper and lower solutions, respectively, at the time K, as the two compartments have the same volume, V. And the diffusion is started with pure solvent in the lower compartment. This equation may be integrated and solved for DJF. The volumes of the upper and lower compartments are not equal, but are Z and V2 respectively. The corresponding relation is the membrane method has been applied in Northrop's laboratory to the study of proteolytic enzymes and of bacteriophage, and in McBain's laboratory to the study of simpler substances, including electrolytes. Between the values of D and M, the logarithms of these values are plotted in Figure 4. The points for substances of high molecular weight show a certain tendency to approach a straight line. Such a linear relation may be obtained by the substitution of appropriate numerical values in the Sutherland-Einstein diffusion equation. This equation may be derived as follows. If a semi-permeable, movable piston is imagined at the boundary between two unequally concentrated solutions of a single solute, as osmosis takes place, this motion could be prevented by the application to the piston of an external force, equal to the product of the osmotic pressure difference and the area of the piston, or AdP. If there is no piston, the concentrations will tend to be equalized by diffusion instead of by osmosis. According to Einstein, the force of diffusion should be equal and opposite to the force required to prevent osmosis, or AdP. If the solutions are dilute, the osmotic pressure will be given by the Van Hoff equation, and the force of diffusion will be RDC. This force acts on the molecules in a thin element of volume. Its volume will be ataxa, and it will contain catax moles or NCx molecules of solute. If n is I number 6.02 × 10 duret, the force acting on each molecule will therefore be RTDCNCD. A force acting on a particle in a viscous medium like water produces a velocity proportional to the force. Hence, the velocity of diffusion may be written if the constant of proportionality is 1. The constant may be called the frictional resistance per molecule. The amount of solute crossing the boundary in the time then T must be equal to the product of the velocity, the concentration, the cross-sectional area, and the time. Or a comparison of this equation with the first form of Fick's law, equation 1, shows that which is the Einstein diffusion equation if the units of the centimeter per second system are used. D must be expressed in C net per C Q-ton and RT in Orange mole, since N is molecules mole, the frictional resistance, has the dimensions of force per molecule and per unit of velocity, or deinsect. The value of is in general unknown, but it would be expected to decrease as docks the viscosity of a liquid when the temperature is increased. For ordinary temperatures, the value of T increases by only 3% for a 10 degrees rise in temperature, while the viscosity of water decreases by about 21%. Actually, the diffusion coefficients for many substank, Iasi and Aqueous solution increase by about 25% when the temperature is raised 10 degrees. While equation for one special case, as Einstein pointed out, the value of in equation 7 is known if the diffusing particles are spherical and much larger than the molecules of the solvent. The frictional resistance is given by Stokes' law, which is the particle. The derivation of this equation may be found in advanced textbooks of physics. Equations 7 and 8 yield the Sutherland-Einstein equation, which was verified experimentally by Svedberg for the case of colloidal gold particles of radius 1/3 milligram. The limitations of equation 9 may be shown as follows. if the dissolved substance consists of spherical particles of radius r and density d. This derivation is also a derivation of Kick's law. Since the limiting law for osmotic pressure is not exact, except for very dilute solutions, it is to be expected that d will vary with c for solutions of appreciable concentration. Molecular weight should be if this equation is solved for r, and the resulting expression is substituted in equation 9. It follows that d should vary inversely as the cube root of m, other factors being constant. For aqueous solutions, the viscosity in equation 9 is that of pure water, or 0.01 in CGS units at y0 degrees Celsius. For substances of very high molecular weight, namely the protein, Svedberg found that the partial specific volume was close to 0.75. Hence, d may be taken as 1.33. The substitution of these figures with the values of known constants yields the simple equation, which should be applicable to dilute solutions of spherical protein molecules at 20 degrees Celsius. The last equation is represented by the straight line in figure 4. As might be expected, this linear graph fails to fit the facts for substances of low molecular weight. Surprisingly enough, the points for sugars fall fairly close to the line. The points for proteins all appear to lie on a line of the calculated slope, but this observed line is lower than that calculated, or displaced to the left by about 0.3 in log m. This means that if m is calculated from d by combining equations 9 and 90a, the calculated values will be about twice as big as those obtained by the ultracentrifuge. Such results were recorded by Anson and Northrop, who suggested that the discrepancies might be due to hydration of the protein molecules, to deviation from spherical shape, or to both factors, the Einstein relation, equation 7. Without the assumption of spherical particles is also used in the derivation of Svedberg's equation for the calculation of molecular weights from measurements of the velocity of sedimentation in the ultracentrifuge. Both this method, which requires an independent measurement of the diffusion coefficient, and the sedimentation equilibrium method, in which the rate of sedimentation is balanced by the rate of diffusion, yield molecular weights independent of molecular shape and hydration. Thus, since the two methods usually give concordant values for the molecular weight, its value as determined by sedimentation equilibrium may be combined with the sedimentation velocity to yield a value for the diffusion coefficient or the frictional resistance of equation 7. The frictional resistance, O, for a spherical particle may be calculated by equation 8, using a value for r based on the molecular weight and the partial specific volume of the solute. If the particles are spherical, the ratio O will be 1. Svedberg has stated that a deviation from the spherical shape, or the existence of hydrated molecules, will make this value higher than unity at Svedberg's values of 44 proteins, range from 1 to 1.9. The difficulties involved in translating these frictional ratios into ratios of molecular dimensions have been discussed by Neurath, who has also calculated values of the molecular weight and frictional ratio for several proteins from measurements of viscosity and diffusion. As a result of revised sedimentation and diffusion data, Svedberg has assigned to egg albumin, formerly believed to have spherical molecules of weight 34,500, a molecular weight of 4,500 or 43, 800 and a frictional ratio of 1.1. If the molecule is not hydrated and is a prolate ellipsoid, that is more like a rod than a disc, Neurath has calculated that its long diameter is about 2.9 times its short diameter for diffusion of electrolyte. In the early days of the ionic theory, Nernst pointed out that although the two ions of an electrolyte may have different mobilities, they are prevented by electrostatic forces from becoming appreciably separated during free diffusion. In other words, the diffusion of an electrolyte may be described by a single diffusion coefficient. Nernst's relation between the diffusion coefficient and the mobilities of the ions may be derived as follows. At the junction between two unequally concentrated solutions of the same electrolyte, there will be a tendency for the more mobile ions to get ahead, producing an electric potential difference d. This potential difference will be established rapidly and will not increase as diffusion proceeds, since electrostatic forces prevent any appreciable separation of oppositely charged ions. Electrical neutrality must prevail in any tangible portion of the solution. The actual rate of diffusion of the electrolyte is due to the combined influence of electric and osmotic forces. Nernst considered a diffusion cell containing two solutions of a completely dissociated, univalent electrolyte, such as HCl. If the cation were free to move under the influence of the potential gradient, its velocity would be L del X, since the mobility U of the cation is defined as its velocity under unit potential gradient. The negative sign means that the motion is opposite to the direction of diffusion if the potential gradient is positive in that direction. The electric force acting on 1 mole of cations is E dx if the E is expressed in volts, dx in centiampere, and F in coulombs per chemical equivalent. This force will be expressed in volt-coulombs per centiampere and per mole of univalent cations. The ratio of ionic velocity to electric force per mole is therefore WFF. It is assumed that the product of this ratio and any kind of force which may be applied to a mole of cations will give the velocity due to this force, since the same sort of frictional resistance is opposing the motion of the ions. If there were no electric forces, diffusion could be considered simply as the result of a gradient in osmotic pressure, as in Einstein's derivation of equation 7. In a thin element of volume, AdX, the osmotic pressure gradient is dP dx, and the diffusion force is AdP. If the average concentration of the electrolyte in this slice of solution is C moles or Cc, this force is exerted on τ moles of ions, including both anions and cations. The osmotic force per mole of ions is therefore dPj dx. If the solutions are dilute enough to follow Van Hoff's law, the total osmotic pressure P is 2IPC, and dPgx is RTdCjx. The osmotic force per mole of ions of either sign is therefore RTdCdx. If this force were acting alone on 1 mole of cations, it will produce a velocity equal to RTdCdx. The actual velocity of the cations must be the sum of the velocities du to electric and osmotic forces, or if V is the mobility of the anion. The osmotic terms have the same sign for the two ions, and the sign is negative because diffusion occurs in the direction of a negative concentration gradient. The electrical terms have opposite signs because of the opposite charges of the two kinds of ions. If the electrical gradient is positive in the direction of diffusion, the cation will be retarded and the anion accelerated. The number of equivalents of ions which will pass a given plane as a result of this motion is given by the product of velocity, concentration, cross-section, and time. Because of the requirement of electric neutrality, this number must be the same for positive and negative ions. It follows that simpler expression is obtained for the amount of substance which diffuses. A comparison of equation 12 with the first form of Fick's law, equation 1 gives the nettest diffusion equation, which is in this derivation, mobility has been expressed in centiampere, c/Watt-ton and force in volt-coulombs. Here, it follows that equation 13 will yield values of d in centiampere. 2 sec bit RTS expressed in volt-coulombs Mach and F in coulomb. Equivalenter, if we recall that mole, and equivalent are identical for univalent ions. The values of the constants in equation 13 are therefore, equation 13 was verified by Ohlm's data for the diffusion coefficients of common 1,1 electrolytes in 0.0 solutions. The observed and calculated values for J have been tabulated by Nernst and others. For halides of the alkali metals, the agreement is within about 0.5%. But for strong acids and bases, divergences of 5 to 10% are shown. Equation 13 was modified by Noyes, as reported by Haskell-Pugh, to cover the case of an electrolyte with ions of valence higher than 1. The factor 2 as a further modification is convenient. In order to make it possible to use the limiting equivalent conductances of the ions Xc and Za in place of their mobilities U and V, since U or V is Xf, the factor 1f must be replaced by 1f. With these substitutions, equation 13 assumes the form which is more generally applicable. If it were possible to have a single electrolyte diffusing without the production of a potential difference, it follows from equation 10 that the amount of cations diffusing across the area and the time dt would be, and by comparison with equations 1 and 14, we may write an ideal diffusion coefficient for an ion of valence Z as follows. Such equations could have real significance for a single electrolyte only if Xe and Xa were equal for the ions of KCl, XCl differ by less than 4%, but no salt is known for which they are exactly equal. To illustrate the difference between such ideal diffusion coefficients for single ions and the real diffusion coefficient of the electrolyte as a whole, we may apply equation 15 to the ions of HCl at 25 theta. Here is 349.8 and Xa is 76.3. The calculated values of DC and Di are 9.31x tangent and 2.03x tangent, while equation 13 or 14 gives 333.3x, known as the actual diffusion coefficient of HCl in a very dilute solution. Evidently, the electric forces produce a marked retardation in the motion of the faster ion and a smaller acceleration in that of the slower. 5. Diffusion in mixed electrolytes. These hypothetical ionic diffusion coefficients have been regarded as limiting values of some real significance in the light of an interesting discovery made by Arrhenius and used by him as additional evidence for the validity of the theory. Electrolytic dissociation. Arrhenius found that the presence of a second solute generally retarded the diffusion of a dissolved substance, except in one special case. When both solutes were strong electrolytes, a marked acceleration of diffusion was observed. This occurred with HCl, for example, when it was allowed to diffuse into water containing nickel, and also when the NaCl concentration was uniform throughout and only the lower layer contained HCl at the beginning of the experiment. Using reasoning similar to that of Nernst, Arrhenius showed that this acceleration could be calculated from the mobilities of the ions and the concentrations of salt and acid in the diffusion layer. Even when the NaCl was initially present at the same concentration in all parts of Tli system, it was necessary to assume that its ions would diffuse. In the case of not, this would be a back diffusion as a result of the electrical gradient produced by the unequal mobilities of 11 plus and Cl. If there were a small backward movement of a large number of Na plus ions, it would be possible for a small number of 11 plus ions to go forward a considerable distance without disturbing electrical neutrality or bringing strong restraining forces into play, even though the Tl ions diffused much less rapidly than the H plus ions. The equations of Arrhenius showed that the acceleration depended on the ratio of salt to acid rather than on the absolute concentration of salt, and this was borne out by his experiments. His calculations also indicated that if this ratio were very large, the rate of diffusion of the acid should approach the calculated limiting value for the H plus ion, and that the liquid junction potential should approach 0. The highest diffusion constants reported by Arrhenius for HCl diffusing into salt solutions were about twice those found in the absence of salt, while the calculated limiting ratio is 2.8. The effect of a salt with an ion in common on the diffusion of an acid was also formulated quantitatively by Abegg and Bose-Chi, who reported qualitative experiments tending to verify the theory. More recently, McBain has studied the acceleration or retardation of diffusion in mixed electrolytes. He found acceleration even beyond the calculated limiting values in certain cases, where one electrolyte diffused against another, or with another into pure water. This was ascribed to the existence of electrical gradients produced by the ions of the second electrolyte. Such experiments are likely to prove useful in explaining the behavior of electrolytes in and around tissues. 6. Diffusion across membranes and ionic distribution. Interesting experiments along these lines were carried out by Rudolf with the object of explaining the distribution of electrolytes between the stomach contents and surrounding tissue. He found that when a small volume of 0.16 N nickel was dialyzed through parchment against a large volume of 0.624 ECl, there was a temporary accumulation of chloride in the salt solution. Its concentration became as high as 0.19 torfia, while that of the outer acid was still 0.16. This unequal distribution of chloride was in the same direction as that observed in a Donin equilibrium when the membrane is impermeable to the positive ion of the inner solution. In a later paper, Rudolf worked out equations for the effect of a steady state produced by the continuous diffusion of an electrolyte between two solutions in which the concentration of this electrolyte was kept at two different but constant levels. He concluded that such a steady state should result in an unequal distribution of the ions of a second electrolyte present in fixed amount, and that the ratios of ionic concentrations for the second electrolyte should follow Donin's equation for membrane equilibrium, even though the membrane was permeable to all the ions present. His deductions were approximately confirmed by the results of a few experiments with simple electrolyte solutions separated by 4 sheets of permeable cellophane DIT. In an experiment in which 0.1 perchloric acid diffused into solution until its concentration was over twice that in the solution from which it came, while the reciprocal of this ratio represented the distribution of Gl ions after the steady state had been attained. 1. Chemical kinetics. This branch of physical chemistry includes the study of the rates of chemical reactions and the factors which influence sucralide rates. The velocity of a chemical reaction may be defined as the rate of decrease in the concentration of one of the reacting substances. The dimensions of reaction velocity are those of concentration divided by time, or in customary use, moles, liters x sec, because of the speed of many inorganic reactions, particularly those between ions in solution. The laws of chemical kinetics were established by the study of slower organic reactions, especially hydrolytic reactions. This class of reactions is of prime importance in biochemistry. The fundamental principle of chemical kinetics is the law of mass action, which was formulated by Goldberg and Wage in 1864 and 1867. Some of the consequences of this law were independently formulated and verified. A chemical reaction is AE proportional to the product of the active masses of the reacting substances, each active mass being raised to a power equal to the number of molecules of that substance which appears in the chemical equation for the reaction. For a reaction which takes place in a uniform environment, the active mass is P proportional to the concentration, and concentrations in moles per liter are generally used in kinetic equations in place of active masses. Goldberg and Wage recognized, however, that only a fraction of all the molecules of each kind would, in general, be in a condition capable of reacting on collision, and that the velocity would then depend on the product of several coefficients as well as on the product of the concentrations. 2 reactions of the first order, if a reaction involves a decrease in the concentration of only one substance. The law of mass action may be written in the differential form where C represents the concentration of the reacting substance and T represents time after the beginning of the reaction. The constant of proportionality Fc is termed the velocity constant, velocity coefficient, or specific reaction rate. Evidently, K would be equal to the actual velocity if the concentration were unity. Since dC is done, equation 1 may be integrated to give the equation in which TO is the initial concentration, or the value of T when T is 0. Reactions whose rates are expressed by equation 1, which contains only the first power of one concentration factor, are called reactions of the first order. Equation 2 is also called the equation for a first-order reaction, or the unimolecular equation. Although reactions which are truly unimolecular in mechanism are relatively rare, the first-order equation applies to many reactions which might appear to be of higher order. Such a pseudo-unimolecular reaction must result if the concentrations of all reacting substances except one are so high that the amounts by which they change during the reaction are mathematically insignificant. WA is the study of such a reaction. The hydrolysis of sucrose in aqueous nitric acid that provided the first verification of equation 2 in the classical experiments of Wilhelmy, who followed the course of the reaction by measuring the optical rotation of the solution. Some of his results, recalculated to give the fraction of sucrose remaining at different times, are plotted in Figure 5, in which the upper curve is a direct plot of this fraction against the elapsed time. The velocity of the reaction is proportional to the negative slope of this curve, and its regular decrease is consistent with equation 1, but is not a specific test of the applicability of the first-order equation. The lower graph is a plot of the logarithm of the reciprocal of the fraction unchanged. According to equation 2, this logarithm should be proportional to the time, and the graph should be a straight line passing through the origin and having a positive slope equal to FC 2.303, if the times are plotted in suitable units. The fit of the points on the straight line is sufficient to illustrate the verification of equation 2, and modern work of greater precision has served to confirm Wilhelmy's conclusion. Wilhelmy noted that the temperature of his laboratory rose from 15.5 to during the first part of this experiment, and fell to 14.5 degrees at the time of the last observation which is shown. This rise may account for the apparent acceleration shown by 2 points. In testing a set of data to find out whether they follow the first-order equation, it is not necessary to calculate the fraction unchanged, or even the actual values of the concentration, provided that some property is measured which varies in a linear way with concentration. Such a property might be the reading of a polarimeter in angular degrees, or the refractive index of the solution, or the total volume of the solution, as measured by the height of the meniscus of the solution in the capillary tube of an atom. If such a property decreases linearly with the concentration, and if R is the reading at time t and re, the reading after the reaction has stopped, equation 2, will be verified if a plot of log, where against is a straight line. The intercept of su line at equals 0 is a measure of the total change, log rho re I, and it is sometimes convenient to determine the value of the initial reading IO by such a linear extrapolation. If the reading decreases as the reaction proceeds, and if the equation fits the data, the downward slope of the semi-logarithmic plot is equal to it, 2.302. Equations 1 and 2 may look superficially different if other notation is used. If x represents the loss in concentration during the time and at the initial concentration, the equations become if I represents the fraction of the substance which has been transformed in the time u equation 2 may be written, and the corresponding forms of equations 2a and 2b may readily be derived. It may be seen by inspection of any of the preceding equations for first-order reactions that the velocity coefficient is independent of the units in which concentration is expressed. In fact, the unimolecular k has the dimensions of the reciprocal of time, or 1 sec time. Equation 2 provides a physical significance for the value of k. It is the reciprocal of that time required for the transformation of a fraction of the original material, such 0.632. It is sometimes convenient to describe the velocity of a reaction in terms of the time required for the transformation of some other definite fraction of the reacting substance. Equation 2 shows that the half transformation time or half period is related to k by the equation, the half period of an unimolecular reaction is therefore independent of the initial concentration. 3. Reactions of the second order. If a reaction involves a decrease in the concentrations of two kinds of reacting molecules, the reaction is said to be bimolecular. Its velocity is proportional to the product of the two concentrations, and if each of these factors is raised only to the first power, the reaction is described by an equation of the second order. The V second order equation assumes a particularly simple form if the initial concentrations of the two reacting species are identical. In this case, the differential equation may be written, and the integral form is equation for hydrolysis or saponification of an ester by an equivalent amount of a strong alkali. The course of such a reaction is illustrated by Figure 6, which was plotted from data obtained long ago by Warder, who prepared a solution containing 0.02 m ethyl acetate and 0.02 m sodium hydroxide, and followed the course of the reaction at 20.526 degrees Celsius by titrating measured samples at intervals. The upper part of the figure is a plot of the fraction remaining unchanged as a function of time, and it shows a smooth decrease in the velocity of the reaction as well as in the concentration of either substance. If this curve is compared with one for a unimolecular reaction, by changing the time scale to bring the curves together at one point, say that at which half of the reaction has taken place, it may be seen that the bimolecular reaction is faster than the unimolecular in the early stages, but slower in the later stages of the reaction. The applicability of equation 4 to a set of data may be tested by plotting the reciprocal of the concentration against the time. The result should be a straight line with an intercept equal to LTU and a slope equal to K. A similar test is shown in the lower part of Figure 6, in which the ordinates are values of KOC. Here the intercept must be unity, and the slope should be Coke. Inspection of Figure 6 shows that Warder's data are well represented by equation 4 throughout at least 85% of the total change. If a bimolecular reaction is started with unequal initial concentrations, A and 5, of the reacting substances, and the change in either concentration in the time t is represented by A, the differential equation for the velocity may be written before this, while ion can be integrated. One must use the method of partial fractions to show that then the integral form becomes this equation, may be tested as a straight line by plotting log against t. A direct plot OYX or HX against for a reaction which follows equation 6 will be intermediate in shape between the up-peak inner curve Ds of figures 5 and 6. If the value of B in equation 6 is very much larger than that of A, it will also be very much larger than any possible value of X. In that case, the ratio HX, H may be considered equal to 1 and cancelled in the logarithm. Equation 6 then becomes identical with equation 2AA, the unimolecular formula, except that the apparent unimolecular velocity coefficient is equal to the product of the bimolecular coefficient and the difference in initial concentrations. HA, it may be seen directly from equation 3 or 5 that any second-order velocity coefficient must have the dimensions of the reciprocal of a product of time and concentration, such as liters, moles, x, sec. In comparing the velocity coefficients of reactions which follow equations of the second order, it is therefore important to note the units used for concentration as well as for time. If the rate of a second-order reaction is expressed as the time for half transformation of one of the reacting substances, the relation between N0.5 and K depends on the ratio of the initial concentration. If this ratio is unity, equation 4 yields the relation if B is greater than A. The half period is a time when X is equal to A. For that case, equation 6 shows that equations for the rates of reactions of orders higher than the second may also be derived from the law of mass action. But such reactions are not often found. Complicated reactions are adject to proceed by a mechanism involving several steps, and the rate is controlled by the slowest step in the series, usually a reaction of the first or second order. Examples may be found in well-known textbooks. For the end of a reaction, in the preceding discussion, it has been assumed that each reaction goes to completion. That is, that the concentration of at least one of the reacting substances becomes zero during the period of observation. The integrated equations, however, indicate that this would theoretically require an infinite time, and this might seem make it impossible to calculate K by a method involving a final measurement of some geometry. For a first-order reaction, it may be calculated from equation 2 that an error of 1 part in 1,000 in the measurement of the total change would produce an error of about 1.5 parts in 1,000 in a value of k calculated from a determination near the time of half transformation, and such an error is not excessive. Hence, it is legitimate to take a reading at 99.9% completion as final. And equation 2 shows that the time required would be about 10 times the half period. In the case of a second-order reaction which follows equation 4, an error of 1 part in 1,000. In the final reading would make an error of about 3 parts in 1,000 in a value of k determined near the half period. And this error is not unreasonable. The time for 99.9% completion, however, would be 999 times that for 50% completion. Evidently, such reactions are best followed by a direct measurement of C for a reaction which follows equation 6. The corresponding calculated values would lie between those obtained from equations 2 and 4, 5. Rails of reversible reactions. If a reaction is reversible, it may appear to stop in a state of equilibrium with finite amounts of the reactants and the products all present. The rate of such a reaction may sometimes be followed in either direction, if both the direct and the reverse reactions are of the first order. The differential equation for the observed rate is this equation implies that the reaction is started with one reacting substance at the concentration, but with none of the reaction product present. At the time T, the concentration of the reactant is T, while that of the product is CQ. C equation 7 is based on the principle that the two opposing reactions proceed simultaneously, and that the rate of each follows the law of mass action. The observed or net rate, dc dt, is equal to the difference B between the rates of the opposing reactions. At equilibrium, the net rate is 0 or the opposing rates are equal, and this coequation may be expressed by the equation which defines the equilibrium constant of the reversible reaction in terms of the initial concentration. 2 and the equilibrium concentration. Ce of a single substance. If Chi is eliminated from equations 7 and 8, the differential equation becomes, and the integral form is equations 9 and 10 differ from the equations for a non-reversible reaction. Of the first order ority in the significance of the constant factor and in the use of a value of Ce other than 0, kinetic experiments do not distinguish between reversible and non-reversible reactions of the first order if the constant is determined from initial and final readings of some property dependent on the concentration. Together with readings at various times during the reaction, such reactions can be distinguished if the actual concentration at equilibrium is determined. In the case of a reversible reaction, equation 8 gives the ratio FCI at 2, while equation 10 yields the sum KHA plus KHA. Hence, a study of the course of the reaction in one direction, together with a knowledge of the equilibrium condition, makes it possible to obtain values for the separate velocity coefficients of the opposing reactions. It may be shown that equations 9 and 10 are still valid when some of the product as well as the reactant is present at the start of the reaction. A similar treatment of opposing bimolecular reactions results in more complicated equations. But again, it is possible to obtain the velocity coefficient of the opposing reactions if the course of the reaction and the equilibrium condition are both investigated. 6. Reaction velocity and temperature. It is well known that most chemical reactions proceed more rapidly at higher temperatures. For any given reaction, a plot of rate against temperature is far from linear, but has a decided upward curvature. The factor by which the rate is multiplied as a result of a rise in temperature of 10 degrees Celsius is sometimes called the temperature coefficient of the reaction. It may be defined by the equation where the subscripts of the velocity coefficients refer to centigrade temperatures. If the factor QHQ were constant over an extensive temperature range, the relation between K and T would be given by a logarithmic or exponential equation, and a plot of log K against T would be a straight line. Represented, it may readily be shown that the slope, 6, is equal to 0.1 log keto for any temperature interval. 2. The linear relation may therefore be written in the form this equation can be used to calculate Keto if the TCM per interval of the observations is not 10. In general, however, a plot of log K against T is not a straight line over a wide range of temperature, and a given reaction will have different values of Keto for different 10 degrees intervals. The left side of where A and B are empirical constants. This equation may be put into the equivalent form if the numerical value, J, of the slope of the linear plot is replaced by Here R is a constant in the perfect gas law, 1.987 calories per mole in 0 degree. EA is ILNUI 4575A, and it has the dimensions of calories per mole. If EA is to be evaluated from only 2 experimental points, equation, LA, may be rearranged to give any of these equivalent expressions, may be called the Arrhenius equation for the effect of temperature on reaction velocity. Such effects are commonly describable in terms of the value of EA, which is called the energy of activation or the critical increment of energy. Arrhenius based his interpretation of EA as an energy of activation upon the following considerations. He knew that the effect of temperature on the equilibrium constant of a reaction was described by the equation in which Q is the heat absorbed, when the reaction proceeds as written in the chemical equation to which the equilibrium constant, GSL, applies. This equation had been derived thermodynamically by Van Hoff for an equilibrium involving perfect gases or perfect solutes. In order to deduce a similar relation for a velocity coefficient, Arrhenius assumed that the ordinary molecules of the reacting substance were always in equilibrium with a small proportion of active molecules, and that the equilibrium constant of this reaction was given by the law of mass action. He assumed further that plume observed rate was determined by the rate of decomposition of the active molecules to yield the products of the reaction, and that this rate followed the law of mass action. The observed velocity coefficient, CC, would then be equal to the product of the hypothetical velocity coefficient for the decomposition of the active molecules and the hypothetical equilibrium constant, K. If FCs were independent of temperature and K were influenced according to equation 12, then the influence of temperature on K would be given by equation Lib, and EA would represent the energy absorbed in the transformation of 1 mole of ordinary molecules into the active state. The Arrhenius hypothesis has been modified by the belief that the active molecules differ from ordinary molecules only in their energy content. But the idea that the slope of the empirical line gives a measure of the energy of activation constitutes the foundation of modern work in chemical kinetics. Numerous examples of the application of the Arrhenius equation to a wide variety of chemical reactions are to be found in special treatises. The Arrhenius equation has also been shown to describe the effects of temperature on the rates of many biological processes. 7. Homogeneous catalysis in solutions. Many reactions which proceed with measurable velocity in a aqueous solution are accelerated by the presence of relatively small amounts of certain substances, which are not, in general, used up by the reaction. Predominant among such catalysts are the hydrogen and hydroxyl ions, which are responsible for the marked effects on reaction rates. For example, the mutarotation of glucose proceeds very rapidly in acid or alkaline solution, but has a zone of minimal velocity extending over a range of pound or 3 units. In this case, the center of the region of minimal velocity is on the acid side of the neutral point. The rates of this and similar reactions may be expressed by an equation of the type where co represents the minimal value of the velocity coefficient, and the last 2 terms represent the catalytic effects of H nano. The direct proportionality implied in equation 13 is consistent with the law of mass action. If a catalyzed unimolecular reaction is treated as a bimolecular reaction in which the concentration of one reactant, the catalyst, does not change. If a reaction proceeded only in the presence of hydrogen ions, we might write the observed reaction as, and the kinetic actuatia would be the value of Q, could then be obtained by dividing the observed velo. as obtained from the simple unimolecular formula by Fn. If the rate were not determined solely by hydrogen ion catalysis, it would be equal to the product of, and the sum of several terms, as in equation 13. The experimental verification of equation 13 is very good for the effect of hydrogen ions, but rather less quantitative for the effect of hydroxyl ions. This uncertainty results from the fact that the catalytic effect of hydroxyl ions is often very great. If it is studied in sufficiently dilute solutions of a strong base, the hydroxyl ion concentration is uncertain because of contamination from the air or from the containing vessel. If the solution is buffered, there may be additional catalytic effects due to acids or bases in the sense of Bronsted, other than 11 plus or OE. These effects are considered in Bronsted theory of general acid-base catalysis. An illustration of the catalytic effects of hydrogen and hydroxyl ions is in aqueous solutions. The hydrogen ion is hydrated to form the hydronium oxoNuN or hydroxorium ion. In the present dissolution, the older name and symbol are used for this ion. The reignition of the state of hydration or solvation of the hydrogen ion is particularly important in comparative studios of reactions in various solvents. Point corresponding to the of equation 13, the true value of AO is probably less than the slope of the line in the right side of figure 8. For Bronskuhl and Guggenheim have pointed out that some of the catalysis observed in these buffers was probably due to ammonia molecules, while Smith-Xiong has found evidence that a large fraction of the catalysis in alkaline solutions may be due to the catalytic effect of negative ions formed by the acidic dissociation of glucose itself. In order to explain homogeneous catalysis, it is assumed that the reaction proceeds through a transition state in which there exists an intermediate compound or critical complex of higher potential energy than that of the reactants or that of the products of the reaction. It was assumed by Bjerrum, as in Arrhenius's original theory of active molecules, that the critical complex is always in equilibrium with the reacting substances, including the catalyst, if such an equilibrium is governed by the classical mass law. In terms of concentrations, the kinetic equation resulting from this hypothesis is identical with equation 14 PRFVL, that the rate depends on the concentration of the critical complex existing at any time. If the hypothetical equilibrium is governed by the thermodynamic law of mass action in terms of activities, an equation of the same form results, provided that the activity coefficients are not changed by the progress of the reaction. On the basis of this theory, a reaction catalyzed by hydrogen ions would be written in the form evidently equations 14 and 15 are of the same form if the ratio of activity coefficients is constant. In comparative experiments with widely different concentrations, especially of electrolytes, this will not be the case. An equation 15 was originally proposed by Bronsted to explain the effect of added salts on reaction velocity. If the substance A is a neutral molecule, the intermediate complex and the hydrogen ion will be ions of the same charge. And the activity coefficient ratio should be decreased by added salt. And the rate of the reaction will show a corresponding decrease. If A is a cation, the complex will be a cation of higher valence, and the activity coefficient ratio will be increased by added salt, which will therefore increase the reaction rate. Salt effects of this kind, either positive or negative, are called primary salt effects, and their magnitude and direction have been shown by Bronsted and others to agree with the Debye-Hickel theory of irotyronic attraction in salt solutions. There are also secondary salt effects. Here, an added salt influences the activity coefficients in a second equili, Rui, such as the ionization of a buffer, and thus indirectly produces a change in the concentration of a substance, such as hydrogen or hydroxyl ion, which is directly concerned in the reaction whose rate is measured. The Bronsted theory of salt effects on reaction velocity has been well verified for solutions of ionic strengths up to about 0.1. For a reaction involving a neutral molecule and a univalent ion, that is, for most reactions catalyzed by ROH, the ironary salt effect at 0.1. Ionic strength is not apt to be more than 5 to 12% of the rate. A secondary salt effect may be of the order of 50% or more under comparable conditions. Electrolyte effects of an altogether different order of magnitude have been found in concentrated solutions of strong acids. In the acid hydrolysis of sucrose, for example, the classical proportionality between reaction velocity and hydrogen ion concentration is strictly exact only for concentrations well below 0.1 mm. The UG per part of Figure 9 illustrates the magnitude of the deviations from linearity observed with concentrated solutions. The velocity coefficient obtained with 4 molar acid is about 600% greater than that which would be expended from the results at low concentrations, as shown by the distance between the observed curve and the extrapolated broken line. The lower part of Figure 9 shows that such a curve may be rectified by plotting the logarithm of the catalytic coefficient of the hydrogen ion against the acid concentration, as has been pointed out by recent workers. This linear relation corresponds to an equation of the form, and it is consistent with the existence of a primary electrolyte effect due to the acid itself, although the effect is far greater than most primary salt effects. This interpretation follows from equation 15 if K is identified with AH, and if the logarithm of this ratio of activity coefficients is a linear function of the ionic strength, as might be expected from a consideration of the ionic types involved. However, Bronsted has not claimed that his equation includes all effects to be found in such concentrated solutions. An interesting relation between reaction rates in very acid solutions and the behavior of basic indicators was discovered by Hammett and Paul. They plotted the logarithms of the velocity coefficients observed for the hydrolysis of sucrose in a number of concentrated solutions of strong acids against a newly defined acidity function and obtained a straight line of unit slope. This result amounts to a linear relation with unit slope between log K and log CB, where BH is the acid cationic form and B is the basic, uncharged form of the indicator. In other words, the velocity coefficient itself was directly proportional to the concentration ratio of the two forms of the indicator, even though this ratio was not simply related to the hydrogen ion concentration, nor to any other measure of acidity which had previously been suggested. Their result may also be taken to mean that KYS directly proportional to UVI septon BZBH, an expression which is of the same form as that given by the Bronsted theory in equation 15. Experiments with reactions catalyzed by acids have brought to light another divergence, usually of lesser magnitude, from the requirements of classical theory as represented by equation 14. This is an effect of the concentration of the principal reactant or substrate on the value of the velocity coefficient. For example, the unimolecular constant for the hydrolysis of sucrose in 0.1 sulfuric acid was found by Jones and Lewis to be increased by about 34% when the sucrose concentration was increased from 10 to 50 G. For 100 cc, a similar effect at lower concentrations of sucrose is represented in Figure 10. Here the rate of hydrolysis at 25 degrees. In 0.48, 6-mole acid hydrochloric acid is contrasted with the rate produced half period was used as a measure of the specific reaction rate because the enzyme reaction does not follow a first-order equation. For the acid hydrolysis, O5 is proportional to the observed values of K. It may be seen that a 5-fold increase in the sucrose concentration produced an increase of about 10% in K for the acid hydrolysis. This effect may well be due to a change in the value of Tuertat in equation 15. The far greater opposite effect which appears in the catalysis by the tenenzyme requires a different explanation. 8. Catalysis by enzymes. Enzymes are organic catalysts formed in living cells. Although no enzyme has yet been synthesized in the laboratory, several have been isolated in crystalline form, presumably as pure substances. The first enzyme to be crystallized was urease, isolated from jack beans by Sumner in 1926. Since that time, a number of proteolytic enzymes of animal origin have been crystallized by Northrop and others. These crystalline enzymes appear to be proteins, but since it is very difficult to apply the ordinary criteria of chemical purity to molecules as large as proteins, some workers still doubt that the crystalline enzymes are pure chemical individuals. When enzymes are dissolved or dispersed in aqueous media, they form colloidal solutions. This property has led some investigators to classify the action of enzymes as heterogeneous catalysis, with emphasis on the possible adsorption of the reacting substances on the surface of the enzyme particles. Other workers, however, have preferred to consider the enzyme solutions as molecular dispersions, laying emphasis on the analogies between enzyme action and homogeneous catalysis, and attempting to apply the laws of classical physical chemistry as in the case of true solutions. The reactions catalyzed by enzymes may be classified roughly as those involving the hydrolytic splitting of chemical linkages, and those involving oxidation reduction phenomena. Theoretically, enzyme reductions, like other catalytic reactions, should be reversible, but such RC reversal has been definitely established in laboratory experiments in relatively few cases. Enzymes which accelerate the hydrolysis of ester linkages have been shown to accelerate the reverse reaction. According to the usual definition of a catalyst, its presence ought not to shift the equilibrium point of the catalyzed reaction. Yet there are many reactions which do not take place at all in the absence of a catalyst, but go to completion if the proper enzyme is present. In such cases, it may be argued that the original rate is not zero, but simply too low for convenient measurement. If so, the reactants with the catalyst are only in false or apparent equilibrium. In other cases, the equilibrium concentrations seem to vary with total enzyme concentration. This may be true if the enzyme is destroyed during the reaction, or if it con-ions with one of the reactants or products. In the latter case, there may be a second equilibrium which should be considered simultaneously with the first. If it is neglected, the first equilibrium will appear to be shifted. There are a few principles governing the action of enzymes which seem to be quite general, and most of these were first established in the study of yeast invertase, also called saccharides or sucrase, an enzyme which catalyzes the hydrolysis of sucrose to form glucose and fructose. This enzyme has not yet been isolated as a pure or crystalline substance, and there is no good evidence that it can accelerate the reverse reaction. The frequency with which this enzyme has been studied is due to the ease with which it can be obtained in highly active and stable form, rather than to its intrinsic importance. But its behavior seems to be fairly typical of that found with other enzymes. 9. Effective enzyme concentration. In general, the velocity of a reaction catalyzed by an enzyme is directly proportional to the concentration of the enzyme. This simple relation was established for yeast invertase by O'Sullivan and Thompson in 1890, and is illustrated in Figure 11. It was formerly believed, Schutz, 1885, that with pepsin the reaction rate increased only as the square root of the enzyme concentration. But Northrop found that direct proportionality could be obtained with pepsin and trypsin if inhibiting substances were first removed by dialysis of the enzyme preparations. 10. Effect of hydrogen ion concentration. If an enzyme reaction is studied in solutions of controlled and varied pF, it is usually found that there is an optimum region of acidity or alkalinity, specific, for the most efficient action of each enzyme on a particular substrate. Such pF effects were first described by Sprenson in 1909. For invertase, pepsin, and catalase, the PLL effect is generally explained, Michaelis and Davidson, 1911, as due to two factors: an irreversible destruction of the enzyme by acid on one side of the UEGUN, and a reversible ionization of the enzyme itself on the less acid side. On this theory, the active portion of an enzyme, such as invertase, consists of the unionized molecules or dipolar ions of the ampho-Cl invertase per leuciteric enzyme. The resemblance between the pH activity curve for invertase on the alkaline side and the dissociation residue curve of a weak acid was confirmed for 3 different temperatures by Nelson and Bloomfield. In the case of pepsine and trypsin, Northrop pointed out that there was a certain parallelism between the PL activity curves and the titration or ionization curves of the proteins used as substrates. In any case, it seems to be well established that the effect of pH on the velocity of most enzyme reactions is described by a curve shaped like a hump. Examples are to be found in books on enzymes. Actual velocity rather than the specific velocity. A quantity proportional to the actual velocity may be obtained by multiplying the ordinates of Michaelis and Mencken. These workers plotted the relative velocity against the logarithm of the initial substrate concentration, and noticed that the curve then assumed the familiar sigmoid form. Characteristic of a mass law equilibrium, such as the dissociation of a weak electrolyte. They were able to derive an equation having such a curve by assuming that there was reversible combination between the enzyme and its substrate, and that the intermediate complex so formed was always in equilibrium, according to the law of mass action with its constituents. They also assumed that the rate of the reaction was governed at any time by the concentration of the intermediate complex, but that the amount of substrate combined at any instant was a negligibly small fraction of the total. So far, their assumptions are identical usually with those used by Arrhenius and Bronsted in explaining homogeneous catalysis. A difference is to be found in their final assumption, which is that the amounts of free and combined enzyme are of the same order of magnitude. If the hypothetical equilibrium is its equilibrium constant, the Michaelis constant, will be where CSE is the concentration of free enzyme, that of the total substrate, and X that of the complex. However, if FV represents the total enzyme concentration, may be obtained from the relation with the result that, or if the rate is proportional to CXEX, this equation makes it proportional to the total enzyme concentration, as it is known to be. While the last fraction accounts for the form of the saturation curve of figure 1, the equation shows that when CQ is much smaller than KMI, X is proportional to C. And while when this is much larger than KMI, X is constant and equal to CT. Evidently, when CS is equal to IWX will be equal to accordingly, the Michaelis constant is equal to that concentration of substrate, which produces half of the maximal velocity. The reciprocal of Kähler-Ammirós is considered to be a measure of the affinity of an enzyme for its substrate. Michaelis and Mencken carried their theory still further by assuming a similar combination of the enzyme with each of the products of the reaction, and worked out an equation for the kinetics of inverse action on this basis. Although this theory has been widely adopted, there are several experimental results which it seems possible variations of the Michaelis theory, which may be applicable to other enzyme reactions, as well as simple graphical methods of obtaining the hypothetical dissociation constants were discussed by Lineweaver and Burke. A kinetic equation formally identical with that of Michaelis and Minton was derived from different assumptions by Van Slyke and Cullen, 1940. They assumed that the time required for the formation and decomposition of the intermediate complex were of the same order of magnitude. The bearing of this hypothesis on the measurement of enzyme activity has been pointed out by Van Slyke, DDR. Van Slyke, Advances in Enzymology, 233 in 1942, in which he has corrected the integrated equations on pages 34, 35, and 39 by substituting X for S12 very rapid enzyme reactions. The majority of enzyme reactions which have been studied in vitro have been relatively slow, with half periods measured in minutes or hours. The range of velocities accessible to experimental study was greatly increased by the development of an ingenious apparatus, Hartridge and Routen, 1923, by which extremely rapid reactions, with half periods measured in fractions of a second, could be studied. The use of this technique led to the discovery of carbonic anhydrase, Meldrum and Routen, 1933, an enzyme which accelerates the hydration of carbon dioxide to form carbonic acid, as well as the reverse reaction. The physiological significance of this enzyme was reviewed by another form of apparatus for recording the progress of fast reactions, was described by Stern and Dubois, who were particularly interested in the enzyme catalase, which is obtained from liver and decomposes hydrogen peroxide. Stern reported the observation of spectroscopic changes, which he interpreted as confirming the existence of a fugitive intermediate complex formed by this enzyme with another substrate, ethyl hydrogen peroxide, in agreement with the theory of Michaelis and Menton. 1. The nature and terminology of thermodynamics. Thermodynamics is that branch of physical science which deals with transformations of energy, particularly of heat and work. Classical thermodynamics consists of deductions made from two fundamental laws, whose general validity is accepted as the result of experience. During the last century, these laws have been usefully applied in physics, engineering, and chemistry, and there is no reason to doubt their applicability to processes which take place in living organisms. Many of the conclusions drawn from thermodynamics are negative rather than positive. It may be shown that a certain process is thermodynamically impossible. If so, it will not occur spontaneously. On the other hand, if a process is shown to be thermodynamically possible, it does not follow that it will occur at a measurable rate. Thermodynamics does not deal with rates, but rather with states of equilibrium. A thermodynamic system usually means a limited portion of space, with the matter which occupies that space. If the system is a closed system, matter is not transferred across its boundaries. If the system is isolated, there is no exchange of either matter or energy between the system and its surroundings. The exchanges of energy between a system and its surroundings, however, are the principal subject of thermodynamic discussions. The state of a system is defined in terms of properties which are measurable on a macroscopic scale. These properties may be the statistical result of the behavior of individual molecules, but thermodynamics does not deal with single molecules. A knowledge of the state of a system implies a knowledge of the kind and quantity of matter, of its distribution between the solid, liquid, and gaseous states, and of the volume, pressure, and temperature. For any homogeneous portion of matter, the last three of these properties are related by an equation of state, which may or may not be explicitly known. In the application of thermodynamics to simple cases, it is assumed that influences of gravitational, electric, and magnetic fields are excluded or may be neglected. A thermodynamic process takes place whenever there is a change, either physical or chemical, in the state of a system. A thermodynamic cycle includes processes by YH. A system undergoes a change of state along one end. The writer is indebted to Dr. Scott Wood of the Department of Chemistry, Yale path, but is returned to its initial state by way of another path. An equilibrium state is one which does not change spontaneously with the lapse of time. Cases are known of apparent but false equilibria, as in a mixture of hydrogen and oxygen gases at ordinary temperatures. Here it may be assumed that the gases are actually reacting to form water, but that the rate is too slow to be measurable. It is well known that the presence of a trace of a suitable catalyst will cause a rapid and violent approach to a condition of stable thermodynamic equilibrium. 2. The first law of thermodynamics. This law is nothing more than the principle of the conservation of energy, applied with the recognition that heat is a form of energy, Helmholtz, 1847. It is conjurized in the statements that the energy of an isolated system is constant, and that any exchange of energy between a system and its surroundings must occur without the creation or destruction of energy. The first law may be expressed by the equation here. Q represents the heat absorbed by a system from its surroundings, and W represents work done by the system on its surroundings. Energy can be transferred only as heat or work if there is no exchange of matter. The function represented by U is called the internal energy. Absolute values of U are not known. Only changes in internal energy can be measured. The expression all means a finite increment in U. It is the difference between the values of U at the end and the beginning of the process which is being considered. For a given change in state, the value of a 7 is independent of the path by which the change takes place. This is also expressed by saying that U is a function of the state of the system, or that do is an exact differential. Similar statements would not be true of Q or W. The amounts of heat and work which are transferred during a change in the state of a system do depend on the path. Unless some special arrangement is made, as in a galvanic cell, the only sort of work done by a system on its surroundings is work of expansion. The term W in equation 1 may then be replaced by P of E if the pressure is PdV, if the pressure varies during the change in state of the system. If a process occurs at constant volume, with no arrangement for the production of electrical or other work, the term U becomes zero. This is the case when a chemical reaction takes place in a constant volume color. The first law then becomes that heat evolved by a reaction which proceeds at constant volume is equal to the decrease in internal energy. If a reaction takes place without any constraint other than that of coetant pressure, the first law implies that the heat absorbed is equal to Al plus PLV. It is possible to state this fact in terms of another thermodynamic function called the heat content or enthalpy, which is defined by the equation the heat content is also a function of the state of the system. If the pressure remains constant, it follows that A is equal to Al plus PAV, or the heat evolved by a reaction in a constant pressure calorimeter is equal to the decrease in the heat content function. The usefulness of this function is due to the fact that most processes are studied at constant pressure. 3. Spontaneous processes and reversible processes. Any system which is not in equilibrium undergoes a spontaneous change in the direction of equilibrium. Familiar examples include the falling of a weight toward the earth, the flow of heat from a hot object to a cooler one, and the diffusion of a gas or a dissolved substance into a region of lower concentration. It is possible to reverse the direction of some of these processes by the suitable application of energy. In thermodynamics, however, any actual or spontaneous process is said to be irreversible because of a special meaning which is assigned to the word reversible. In order for a process to be thermodynamically reversible, it would have to be possible to restore the system to its original state by the expenditure of only as much energy as had been lost by the system in the original process. Conceivably, this might be true for the expansion of a gas in a cylinder provided with a U-perfectly fitting but frictionless piston if the external pressure were infinitesimally lower than that of the gas. The reversible process is an ideal which is approached only by small and slow real changes, when frictional and other forms of resistance are negligible. An infinitesimal change from a state of equilibrium is considered to be reversible. The concept of a reversible process is useful in the calculation of limiting values for the energy changes which accompany real process. 4. The second law of thermodynamics. This law states a restriction which has been observed in the transformation of heat into work. This restriction has been stated by Planck as follows. It is impossible to construct an engine which will work in a complete cycle and produce no effect except the raising of a weight and the cooling of a heat reservoir. This law denies the possibility of perpetual motion of the second kind, by which work would be produced from heat without other changes. It does not deny that work can be produced from heat by means of a suitable heat engine, for in this case there is always a transfer of a considerable fraction of the heat absorbed from a hotter to a cooler portion of the surroundings. It was shown by Carnot, 1824, that the theoretical maximum work done if Chi is the heat absorbed at the higher temperature Ti. This maximum work could be obtained only if every step in Ti operation were thermodynamically reversible. If such an ideal heat engine is considered as a thermodynamic system, the completion of a cycle restores the system to it as original state. The value of Atia is therefore 0 for any number of such V's. It follows from the first law that where 72 is the inat given up to the reservoir at the lower Tc temperature, T2H equations 5 and G may be combined to give a relation which is valid for a cycle involving the reversible transfer of heat between two parts of the surroundings at different temperatures. This may be put into the form for any reversible cycle, The sum of such ratios, GS-ET strati, for any RC-versible process was termed by Clausius, 1854, the increase in entropy of the system. Changes in the entropy and accompanying a reversible process are defined the fact that, as is zero for a cyclic process, is consistent with the idea that the entropy is determined by the state of the system, and it can be proved that the change in entropy, like the change in internal energy, is independent of the path by which a definite change in state occurs. If the cycle of a heat engine includes an irreversible process, the work done is less than that given by equation 5, for some heat is lost by frictional or other resistance. Since E2 is greater than before, ZQT is less than 0, because the process is cyclical and EE is a function of the state of the system, as is still 0. It follows that for a cycle which includes an irreversible process, and it can be shown that this inequality is valid for any irreversible process, whether it be cyclical or not. The change in entropy accompanying an irreversible process is not given by the sum of the actual QT terms, but must be obtained from the corresponding terms for a reversible process which produces the same change, e.g. state. In terms of entropy, the second law of thermodynamics is comprised in the relations 9 and Cl if changes in the entropy of the surroundings as well as of the system are considered. This law may be stated in the form that any irreversible process is accompanied by an increase in the total entropy of all bodies concerned in the change, while a reversible process takes place with no change in entropy. 5. Work, content, and free energy. An alternative statement of the second law, in terms of work rather than heat or entropy, was once made of doing work. To reverse any such process requires the expenditure of work from outside. The significance of this statement was clarified by the use of two additional thermodynamic functions, which had been employed by Gibbs in 1875. The work content, maximum work function, Helmholtz free energy and the free energy, and the free energy F thermodynamic potential Gibbs free energy, are defined by the equations. These equations indicate that each of these quantities is a definite function of the state of a system. For a process which takes place at constant temperature, the change in A is if the process is reversible. Equation 13 may be combined with equations 1 and 9 to give, since the work done by a reversible process is the maximum work which can be obtained from a given change in state. If the same change in state takes place along a path which is not completely reversible, the decrease in A will be the same, but the work done will be less. The work done approaches the decrease in A as the process becomes more temporally reversible. For a process which takes place at constant temperature and at constant pressure, the change in F is if the process is also reversible. Equation 15 may be combined with equations 1 and 9 to give the decrease in free energy accompanying any process at constant temperature and pressure is equal to the maximum net work, exclusive of work of expansion. If the J process is not completely reversible, the decrease in free energy is greater than the actual giant work, which approaches F as the reversibility of the process is improved. Since any spontaneous process is thermodynamically irreversible, such a process will yield an amount of work less than that obtainable from the same change of state by a reversible path, instead of equations 14 and 16. The inequalities are valid for spontaneous processes in the absence of any arrangement for the production of electrical work, or some other unusual form of work. The term phi represents mechanical work of expansion and is equal to PAV. If the volume of the system is kept constant, this work term becomes 0. Spontaneous processes may therefore be characterized by two additional inequalities. A spontaneous process at constant temperature and volume must be accompanied by a decrease in the value of the work content, while one which occurs at constant temperature and pressure is possible only if the free energy decreases. Either process can be reversed only by the expenditure of energy from outside the system. Spontaneous processes tend to go on until equilibrium has been attained. When this state has been reached under the given conditions, the value of O or F will no longer change. The equations may therefore be used as criteria of equilibrium. These and other criteria corresponding to other restricting conditions were stated by Gibbs, but it was Lewis who pointed out the practical advantage of using relations containing the free energy function. This advantage arises from the fact that most processes are studied at constant pressure. As a result of Lewis's work, our knowledge of chemical reactions has been greatly increased by the systematic study of free energy changes. 6. Chemical potentials. For an infinitesimal reversible change, in which the only work is that of expansion, equations 1 and 9 may be combined in the form G and Lewis and M. Randall thermodynamics and the free energy of chemical sub. If such a change involves the introduction of additional quantities of matter into the system, there is an additional increment in internal energy for each added substance. Equation 23 must then be replaced by the expression in which UI and OA2 represent the quantities of different substances in the system. Each of the coefficients G is a partial derivative of U with respect to the amount of one substance only. If the change takes place at constant temperature and pressure, the increase in free energy, according to equation 12. His addition of equations 24 and 25 gives the relation from which it pairs that G is also a J Arleal derivative of F with respect to the amount of a single substance. Two coefficients G were first used by Gibbs, who referred them to unit masses of substances. If the unit mass of each substance is taken as its molecular weight in some specified state, and represents a number of moles, and EI is the chemical potential per os, which is identical with the partial mole of free energy of Lewis. For a change which does not involve the introduction of new matter into the system, but only the transfer of matter from one phase to another, the corresponding relation is where the prime marks refer to two phases. If only one kind of matter is transferred, eaten as equally, and if the system is in equilibrium, EDFTP is 0. It follows that the simple relation is a criterion of equilibrium for the distribution of a substance between two phases. The chemical potential is a measure of the tendency of a substance to pass from one J-has to another, that is, of its escaping tendency. Equation 28 applies to the equilibrium between a liquid and its vapor or solid phase, and to that between a pure substance and its saturated solution. It also provides a basis for the law of distribution of a solute between two solvents, as well as for the equations describing osmotic equilibrium and the Donen membrane equilibrium. The chemical potential was employed by Gibbs in the deduction of the phase rule, and it has also been used to deduce many other fundamental laws of physical chemistry, including the law of mass action for physical or chemical equilibrium. Numerical values of the chemical potential, however, are not often used. For a dissolved substance, the chemical potential has the inconvenient property of approaching minus infinity as the concentration becomes very low. It is preferable for many chemical calculations to replace the chemical potential by a related function, the activity, 7, activity, and activity coefficient. In eerie applications of thermodynamics to physical chemistry, Van Hoff, Nernst, and others, important equations were derived by combining the first and second laws with the equations for perfect gases or ideal, dilute solutions. These equations were exact only when applied to highly dilute systems. Equations of similar form were made applicable to all regions of concentration by the introduction of a function called the activity, Lewis, 1907. The activity of the substance may be defined by the equation in which it represents activity in R is the constant of the G-Urfeck gas law. The quantity is the chemical potential of the substance in an R arbitrary standard state in which its activity is taken as unity. The standard state is chosen in such a way that the activity becomes equal to the pressure for a perfect gas, to the mole fraction for the solvent in an ideal solution, and to aqueous solution. The activity of a pure solid or liquid is taken as 1. The activity may always be replaceable by the product of an actual pressure, mole fraction, or molality, and a number called the activity coefficient. The activity coefficient is an expression of the difference between actual and ideal behavior. If the laws of ideal gases or solutions were accurately followed, the activity coefficient would always be 1. Actually, its value is within a few percent of 1 for most gases at moderate pressures up to 1 or 2 atmospheres, and for non-electrolytes in aqueous solutions of moderate concentration, up to about 1 mole. For strong electrolytes in aqueous solution, however, marked deviations may appear at much lower concentrations. Approximate values for some common salts in water at 25 degrees are given in methods for obtaining the values of activity coefficients were discussed. One of the simplest ways of determining the activity coefficient of a dissolved substance is based on solubility measurements. Since the chemical potential of the solute in a saturated solution is equal to that of the solid saturating body, the activities of the same substance in the two phases are proportional, or it will be seen that equation 30 is nothing more than the law of mass action, as applied to a simple case of physical equilibrium. The value of K would be 1 if the same standard state were used for both phases, but this is not the case. The activity of the solid is taken as 1. That of the dissolved substance may be replaced by the product of its molality, W, and its activity coefficient, 7, or by the product of its molar concentration. Accordingly, we may write the solubility may be varied by equilibrating the solid with solvent containing varied amounts of a second solute of concentration C by a suitable plot, for example, log C versus C plus C or EAC plus. It may be possible to make a linear extrapolation to infinite dilution. This procedure yields a fictitious value, C9, for the solubility of the first substance at infinite dilution of both substances. Co is equal to K equation 31, since the value for infinite dilution is 1. The activity coefficient of the first substance in a solution in which its solubility is C is then obtained by the simple relation 8. Osmotic work and free energy of dilution. In the historical development of physical chemistry, considerable use was made of the concept of maximum osmotic work and of the analogy between the behavior of dilute solutions and perfect gases. If a gas is allowed to expand reverse Bly, the maximum work done on the surroundings is GP/dV. If the gas follows the perfect gas law, P may be replaced by NLTV, and if the temperature is constant, the work done is where N is the number of moles of expanding gas. If a solution is separated from the pure solvent by a semipermeable piston, it may also expand reversibly, drawing in solvent by osmosis. If the D.A. Maffin's Principles of Electrochemistry, Reinhold, New York, 1939. External pressure on the piston is infinitesimally lower than the osmotic pressure of the solution at all times during the process. The maximum work done in raising the piston is given by a similar integral in which the osmotic pressure P replaces the gas pressure P if the osmotic pressure follows V at T equal to unRT or TC. Accordingly, the maximum work obtained by such a reversible dilution process is also given high ideation 38 if N is taken as the constant number of moles of solute in the system. If the external pressure on the piston is increased above the osmotic pressure of the solution, the latter becomes more concentrated by the removal of solvent through the semipermeable piston. In this case is less than C2, W is negative, and work at least equal to W must be done on the system by some external agency. If the pure solvent and the piston are removed, the change of state may be described by saying that N moles of solute have J as from the condition described by Ci and T to that described by, and the initial and final total pressures being identical with that of the atmosphere. Now, N moles of solute may also experience the same change of state by being transferred bodily from a large volume of solution of concentration 6 to another large volume of solution of concentration. If this transfer is accomplished in a reversible way, the J process will yield an amount of energy equal to the W of equation 33. And this change in energy has often been called osmotic work. Since is the maximum work obtainable from a process at constant temperature, it is also equal to IL for the whole system, according to equation 14. The change in energy accompanying the transfer of a solute from one concentration to another is better expressed in terms of free energy and activity. because it is then no longer necessary to limit the equations to the case of solutions which follow Wyckoff's law for the reversible transfer of n moles of solute from solution to solution. The decrease in free energy at constant temperature and pressure is given by an equation similar to equation 27. The chemical potentials may be expressed in terms of activities by equation 29, with the result that if the activity coefficients of the solute in the two dot solutions are identical, the right members of equations 35 and 33 are the same phi. Actually, the changes in free energy and work content must differ by a PVI, but in the application of equation 33 transfer of solute, it was assumed that no change in volume or pressure occurred. Equation 35 was used by Borsuk and Weingarten in an interesting application of thermodynamics to the calculation of the work done by the H. Borsuk and H. M. Weingarten. Pro Nat Acad St. S. 17-3-13-1931. Human kidney in the formation of urine. These authors showed that their equation could be reduced by simplifying assumptions to the form of an equation previously obtained by Hill, who made use of the concept of osmotic work rather than free energy. 9. Some thermodynamic equations of physical chemistry. A few of the physical-chemical relationships, which have been deduced by means of thermodynamics, are summarized below. Derivations of these equations are to be found in textbooks of physical chemistry and chemical thermodynamics. The law of mass action is an exact equation. If the parentheses refer to the activities at equilibrium of the substances whose symbols are enclosed, free energy of a chemical reaction. Here K is the equilibrium constant, as defined by the preceding equation. Q is a similar quotient of activities which do not refer to the equilibrium state. These activities are specified or implied in the chemical equation for the process, which is the complete conversion of the indicated numbers of moles. Free energy and temperature. Here F and all refer to the same process at constant temperature and pressure. Equilibrium, instant, and temperature. Oniji, this equation, all refers to the process indicated by the chemical equation for which K is calculated. Vapor pressure and temperature. Here, R refers to the formation of 1 mole of vapor from the liquid or solid, and AV is the corresponding increase in volume. The second form is exact if the volume of the liquid or solid is negligible with respect to that of the vapor, and if the vapor behaves as a perfect gas. Osmotic pressure and vapor pressure. This equation P is the osmotic pressure of a solution over which the vapor pressure of the solvent is P. Po is the vapor pressure of the pure solvent, and VQ is the molar volume of the liquid solvent in the solution. The equation is exact if O is independent of pressure, and if the vapor of the solvent follows the perfect gas law, osmotic pressure and concentration. Here X is the mole fraction of solute in the solution. The quotient is exact if the conditions for the preceding equation are satisfied, and if the vapor pressure follows Raoult's law. The simpler equation of Morse gives values of P which are somewhat higher, but the difference is less than 1% for concentrations below 1 mole. For concentrations of the order of 0.1, either equation becomes practically identical with the original equation of Van Hoff. None of these equations is valid for electrolytes unless the concentration of the ions is taken into account, and even then it may be necessary to introduce an empirical osmotic coefficient to make the equations fit experimental data. Freezing point depression and Kosevenz-Andreas-Aveni. This is an approximate equation for dilute solutions. For QS solute osmotic pressure and freezing point depression, this equation is valid over a much wider range than the preceding formula. For aqueous solutions, it may be written electromotive force and temperature. In this equation, E is the electromotive force in volts of a reversible galvanic cell. Always the increase in heat content in joule of the cell reaction, which involves an electrochemical equivalence, and F is the Faraday, 96,500 coulombs per equivalent. Other thermodynamic relations involving electromotive force are discussed in the following chapter. G.N. Lewis and M. Randall, Thermodynamics, and the free energy of chemical substances. L. E. Steiner, Introduction to Chemical Thermodynamics, Traw Hill, New York, 1941. Ile History and Electroplyziftogy male, said to have had human origin. Shortly before 1800, in the well-known experience of Ivani with frog's legs in contact with two metals. And in the controversy at Jean, Hilvani, and Volta concerning the interpretation of these experiments. Ried's dispute led Volta to the discovery of the first electrochemical cell, the voltaic isle. Electrochemistry has developed along quantitative lines since the Statiaphore Faraday's law, 1833, while the modern development of electrophysiology dates from the discovery by D. Bois-Reymond, 1843, of the CRR injury from a muscle or nerve. In recent times, much, the XPXPMI mental work, in both of these branches of science has involved fluid measuriquid of electromotive force. If a single P, say of metal, is connected at 2 points to the terminals of an instrument for measuring electromotive force of potentiometry, there is in general no difference in electrical potential. The electromotive force is zero. Yet the only sort of potential difference which can all be assured is one existing between two ices of metal of the same kind. If there are connected between these two pieces of similar metal one or more pieces of dissimilar metal, there may be a measurable electromotive force. If two of the junctions are kept at different temperatures, this arrangement is a thermocouple. A measurable electromotive force may also be obtained from a cell containing two electrodes of different kinds of metal, both in contact with a C-Egliet solution of suitable E-Henkel nature. Kyle, Shistence of this electromotive force does not require a difference in temperature. Such an arrangement is a galvanic cell. Again, the measured electromotive force is that between two UIEs of metal of the same kind, namely the wires leading to the measuring instrument. Bloom electromotive force is G, narrowly considered by chemists to be due to unequal potential differences at the phase boundaries in the cell, that is, the interfaces between each of the electrodes and the solution. It should be emphasized at the outset that no way is known to measure the single potential difference at any such phase boundary. Of the galvanic cells which are employed in physicochemical investigations, the majority have electromotive forces of the order of 1 volt or less. The Km of the lead storage cell or accumulator is about 1 volts. That of a fresh dry cell is about 1.5, and that of the Weston Standard cell is close to 1.018. Potentiometers used in the exact measurement of EMF have a range extending to 1.6 volts, and this range has been found ample in most scientific investigations of individual galvanic cells, too. In certain cases, the free energy of a chemical reaction may be obtained from the measurement of the electromotive force of a reversible galvanic cell. This is possible if the cell is what Gibbs called a perfect electrochemical apparatus. That is, if no change takes place in the cell except during the passage of current, and all changes which accompany the current can be reversed by reversing the current. The electromotive force of such a cell, if measured at constant temperature without drawing current from the cell, is proportional to the free energy of the cell reaction. If a very large cell of this sort were allowed to deliver n Faradays of electricity, the cell reaction would proceed reversibly in the direction of spontaneous approach to equilibrium. The I number n is the number of electrochemical ECPVHUTs corresponding to the numbers of moles indicated by the chemical cell reaction, since electrical work in joules is given by the product of electromotive force in volts, and the number of coulombs of electricity which flow. The maximum electrical work of the process is 7, where F is the number 96,500 of coulombs in 1 Faraday of electricity. The maximum work of the process is This includes any work of expansion as well as the electrical work. It follows from equations 14 and 16, chapter 3, since only these two kinds of work are involved, that the maximum Yeah, electrons. And the activities of the substances involved the cell reaction is for 1 Faraday of electricity. The activities of the two solids and the hydrogen gas are unity by definition. Equation 37, chap. 3 may be applied in the form in which K is the equilibrium constant and P is the product of the activity coefficients of the ions and Cl equations 1 and 2. May be combined to give a formula for the electromotive force. The quantity EO is a constant characteristic of the cell reaction at the given TMF aperture. Its value may be obtained by an extrapolation to zero ionic strength of a suitable function of the EMF. And the ionic concentrations in using equation 3 is generally expressed in volts. If so, R must have the value 8.314 joules per mole and per degree. If logarithms to the base 10 are used, the coefficient of the logarithmic term is 1.98 10. The numerator of this expression is 0.059150 for 25 degrees or 0.06. In subsequent equations, this coefficient will be abbreviated as 0.06 with the understanding that its exact value should be used in calculations. After EQ has been obtained, equation 3 may be solved for OAFLD. Cells of type I, reversible galvanic cells without liquid junction, have been widely used by physical chemists in the measurement of the activity coefficients of strong electrolytes and the dissociation constant of weak 3. Concentration cells without transference. If two cells of type I are connected in series with like poles together, the resulting double cell is called a concentration Cu without liquid junction or without transferency. If the concentration of the electrolyte is the same in both parts of the cell, the electromotive force will obviously be zero. If two different concentrations are used, a finite electromotive force is obtained if current is drawn from the cell. The same reaction proceeds in opposite directions in the two parts of the cell, and the net result is the removal of ions of the electrolyte in equivalent amounts from one solution and the production of similar ions in the same amounts. In the other, this transfer is not called transference in the electrochemical sense because the ions do not migrate directly from one solution to the other. In this case, hydrogen, silver, and silver chloride will also appear or disappear on one side or the other. Since each of these substances is in the same state in the two parts of the cell, the changes in their amounts do not involve a change in the free energy of the whole system. The free energy change of the net cell reaction is therefore that of the transfer of the electrolyte from the more concentrated to the more dilute solution. It is given by the difference between two equations of the form 2, or by the sum of two equations like 35, chap 3, one for each type of ion. The electromotive force of the cell is therefore related to the concentration of the acid, since GH and CaCi are equal in this case, by the equation where the subscripts refer to the two solutions and dura is the geometric mean activity coefficient of the two ions for concentration cells with transference. CH of this type has two identical electrodes reversible with respect to the same kind ions, and two solutions containing the same electrolyte at two different concentrations. The cell is completed by a direct Li-Uid junction La-Winu in the two solutions. Such a cell is in its cell reaction involves not only the changes at the electrode, but the migration of the ions at the Lippi junction. The electromotive force therefore depends on the transference number or the fraction of current carried by one kind of ion in this direct migration. For small differences in concentration, the electromotive force is given Ti and E, Waishori obtained from equation 35 chapter 3. By replacing Ti by here, ELA is the transference number of the ion to which the electrify are not orsivitetable, in this case the anion. Since the transfer number is related to the mobilities U and R of the cation and anion of an electrolyte by the equation G may be written these equations, without activity coefficients, were obtained by Nernst in 1880. If U and V were exactly equal, equation 7 shows that would be 0.5, and equation 6 or 9 would then reduce to a form resembling the simple formula, which is more commonly associated with Nernst's name. Liquid Junkleon potentials. In the case of hydrochloric acid, the transference number of the anion is only 0.17. That is, the hydrogen ion is about 5 times as mobile as the chloride ion. At the junction between two solutions of hydrochloric acid, both ions diffuse from the more concentrated solution to the more dilute. The Lie mobility of the hydrogen ion has the effect of increasing the Uloslev electric potential of the dilute solution, even though electrostatic forces represent any analytically detectable separation of the oppositely charged ions. The existence of this diffusion potential may be inferred from the fact that the electromotive force of Celtica with 0.1 and 0.0 solutions of the acid is only 19 millivolts at 25 degrees, while that of the similar cell with silver-silver chloride electrodes is 92.5 MB2. In the first case, the liquid junction potential opposes the difference in electrode potentials, while in the second case, it is added to it. In this argument, it is implied that the difference between the electrode potentials ought to be the same for the two cells. This would be the case if the hydrogen and chloride ions in a given solution of hydrochloric acid had identical activity coefficients. If this assumption could be justified, we could say, in agreement with Nernst, that the first term on the right in equation 9 RCA represented the difference between the electrode potentials, while the last term represented the liquid junction potential or diffusion potential. The Rohrer is just half the electromotive force of a concentrated cell without transference, since this cell has an EMF of 111.8 MV. With these concentrations of acid, the diffusion potential would be calculations rest on an assumption which has not been verified. No way is known to obtain the activity coefficient of a single kind of ion, nor to obtain the value of a single junction potential. If one could be measured, the other would be known. Any value for either quantity rests on an arbitrary assumption. Various J.A. Fausable assumptions lead to calculated values for the same liquid junction potential, differing by 1 or 2 millivolts, even in simple cases. For a cell containing solutions so nearly alike as to have the same activity coefficient, Nernst's original interpretation would be core CT, and the diffusion potential between two dot solutions of the same 1,1 electrolyte would be, this is the integral form of equation 11 channel, which occurred in Nernst's derivation of the relation between diffusion coefficient and ionic mobility. It was later pointed out by Nernst in 1898 that the diffusion potential in a cell of type 2 could be practically eliminated by using as the solvent not pure water, but a solution of a suitable indifferent electrolyte. According to more recent ideas, a second electrolyte, if present in sufficient concentration, will have a swamping effect on the forces between the ions of the first electrolyte, giving it a constant activity coefficient independent of its own concentration. In that case, equation 9 becomes which is the original Nernst formula. The swamping effect of an added salt was also shown by Bronsted in 1919 to make the classical law of mass action in terms of concentrations valid for reactions involving ions. It is this influence of a relatively constant electrolyte content which has made possible the application of simple equations in studies of the acid-base balance in blood. In spite of the uncertainty as to the exact measurement of liquid junction potentials, fair estimates of their probable magnitude may be obtained from these equations based on the laws of ideal dilute solutions. A comparison of equations 10 and 11 shows that the diffusion potential in a concentration cell with transference is less than the calculated difference in electrode potentials. The latter may approach 60 MV. For a 10:1 ratio of concentrations, while the diffusion potential is calculated to be about 36 MV. Dilute solution positive for hydrochloric acid plus 12 MV for sodium chloride and only about 1 MV for potassium or ammonium chloride solutions. For the case of two equally concentrated solutions containing different union electrolytes with a common ion, The diffusion potential may be calculated approximately by an equation of Planck, 1890, modified by Lewis and Sargent, 1909, in which Ai and A2 are the equivalent conductances of the two electrolytes at the given concentration. The sign of AR may be obtained by considering the relative mobilities of the ions not shared in common. At the junction between 0.1 solutions of hydrochloric acid and sodium chloride, the salt solution will become more positive by about 33 MV. At the junction of 0.1 N sodium chloride with 0.1 potassium or ammonium chloride, the former solution will be positive by about 5 MV. These calculated values indicate that the potential difference at a free junction between two solutions is hardly of sufficient magnitude to account for the injury potential in muscle or nerve. Such bioelectric potentials are of the order of 50 MV, and they occur in the absence of any high concentration of 2Te or OHe, the ions of highest mobility. 6 salt bridges. In the case of potassium chloride, it happens that the two ions have nearly equal mobilities. The transference number of the cation is close to 0.49 at all concentrated. If a concentrated solution in the salt is interposed between two solutions containing other electrolytes at much lower concentrations, most of the diffusion at the boundaries will consist in the movement of R and Cl ions at nearly the same rate. Hence, it might be expected that a salt bridge of saturated potassium chloride solution would tend to obliterate diffusion potentials. If the hydrochloric acid solutions of cell 2, 0.1 and 0.01 are not connected directly, but only by means of such a bridge, the electromotive force at 25 degrees becomes 57.4 MV instead of 19.3 MV. If this procedure canceled diffusion potentials, the electromotive force of the cell NCl had the same activity coefficient. The electromotive force would then be this set of assumptions, thus leads to a result which is only 1.5 MV below the observed value. This is an extreme case because of the unusually large difference between the mobilities of H plus and ClF. The limiting conductances of ions are proportional to their mobilities. Some approximate values for Tns not containing a high concentration of OH differences in ionic mobility are small. It is therefore inferred that if solutions of moderate acidity or alkalinity are connected by a salt bridge of saturated potassium chloride solution, the elimination of the diffusion potential will be nearly complete. This assumption forms the basis for the common use of the salt bridge in measurements of PLL and of oxidation reduction potentials. 7. The Delernin of PLL values. If the solutions of cell 3 are replaced by a solution of known PLN, one whose PA is to be determined, the cell becomes E2EL unknown pH2KL, SAD, standard 5s2. Under suitable conditions, the hydrogen electrodes may be replaced by junhydrone electrodes or glass electrolytes. If liquid junction potentials are eliminated by the salt bridge, the electromotive force of cell 4 Phi will be given, in which the activities are those of the hydrogen ion. If pH is interpreted as log A, this equation may be written equation 14, may be used as an experimental definition of pH if the value for a standard solution is agreed upon. This is essentially the common practice. One suitable standard solution is 0.1 acetic acid and 0.1 sodium acetate. Its pH has been located as the result of two investigations within 0.0, one of 4.645 at either 25 degrees or 38 degrees Celsius. Actually, the use of cell 4 is less convenient than that of a cell composed of a single hydrogen or glass or quinhydrone electrode and a calomel half cell, in which EO represents the electromotive force which would be obtained if the hydrogen electrode were bathed by a solution of pH 0. The behavior of the electrodes may be checked by measurements with one or more standard solutions. The difference between two such values of the electron force of cell Vifi as equivalent to the E of cell 4, in equation 14, may be written in the form for this case. The practical value of PTI determinations, irrespective of any theoretical significance, is now widely recognized by industrial as well as biological chemists. The standardization of the DL scale is of some ITAR-QQ ordinance in the comparison of PTI values from different sources, and in the use of PPL values in equations involving dissociation constants of electrolytes. I.e., most common equation of this type is the application of the law of mass action to a buffer system Henderson-Hasselbalch equation. This equation is generally written. It must be used with the understanding that UL salt refers to the concentration of a completely dissociated salt of an acid so weak that the concentration of its undissociated molecules is practically equivalent to its total concentration, DACID. In the case of carbonic acid, DACID means the concentration of free dissolved CO2, whether hydrated to form H2CO3 or not, as obtained from a solubility coefficient and a measurement of CO2 tension, while ESalt means the difference between the total CO2, bound or free, and this value for the free CO2. The quantity pK is the negative logarithm, not of the classical constant pKi, nor of the true thermodynamic constant TTKy, but of an apparent ionization constant EAK, obtained from pH measurements under similar conditions of temperature, ionic strength, and concentration of other solutes. Evidently, pK is the value of pH when the ratio U-salt acid is unity, and its value is therefore dependent on the standardization of the pH scale. At the present time, most pH measurements are made by means of the glass electrode. The technique and principles underlying the successful use of this important tool have been fully discussed by Dole. The most useful earlier work on pH measurements and buffer solutions is that of Salark-Vadbad, the shorter book of Kolthoff and Leightonens may also be recommended to students of these subjects. 8. Membrane potentials in systems at equilibrium. If a membrane germule to some component psi are at its two parts of a system, and the system is in equilibrium, the chemical potentials of a permeant substance in the two phases must be equal, as indicated by equation 28. This means that where Tli prime marks refer to the two J-Hases Sage are rated by the membrane. The chemical potential of a strong electrolyte is the sum of the chemical potentials of its ions, or if of the combining equations 17, 18, and 29, chapter 8. We may obtain a relation between ionic activity J rhodix. For sufficiently dilute solutions, the activity coefficients for the two phases may be considered identical, and equation 19 takes the form which is typical of the law deduced from membrane equilibria by Donkin 1911. 1911. If the membrane is permeable to all subslength, each resent, there will be no difference between the two phases at equilibrium, and there will be equality of the individual ionic concentrations as well as their products, however. If one haze contains an additional electrolyte Rachial, whose cation cannot penetrate the membrane, the requirement of electric neutrality in this solution demands an inequality between TCI and CI. For this sort of unequal distribution of diffusible ions is characteristic of the condition known as the Donan equilibrium. For systems composed of a protein hydrochloride in aqueous hydrochloric acid, separated by a collision membrane from aqueous hydrochloric acid containing no additional substance, relations 20 and 28 were amply confirmed by the extensive W.M. Lark, the determination of hydrogen ions. Williams and Wilkin, Baltimore, experiments of Loeb, Gauge approximate figures for CN were obtained from pH measurements, while those for FCI were obtained by volumetric analysis for total chloride, as well by electrometric methods. If such a system is provided with electrodes reversible to one type of diffusible ion in both phases, thermodynamic equilibrium implies that the electromotive force must be zero. Loeb's experiments fulfilled this requirement, as shown by measurements with silver-silver chloride electrodes. The same would be true if hydrogen electrodes were used. As in the CEL, when the solutions were removed from contact with the membrane and put separately into a pH cell, a difference in pH was found, amounting in some cases to 0.6 pHu. This difference means that in the cell, the hydrogen electrode in the external acid was J-oxidative by Luarli at 6 millivolts. In some cases, Loeb also made measurements of the cell, which is commonly regarded as yielding a measurement of the membrane potential. This cell is illustrated in Pig 13. A comparison of sets to 6D and indicates that the EMF of cell 8 must be equal and opposite to that of cells A7 if equilibrium prevails, and this is what Loeb found in numerous experiments. For the Donnan membrane potential, the EMF only therefore followed the Ishiuishi, and the electrode connected to the external acid solution was negative. In experiments in which the hydrochloric acid was replaced by sodium hydroxide, the polarity of both cells 7 and 8 was reversed. This is a result of the amphoteric nature of proteins which form negative non-diffusible ions in alkaline solutions. Further experiments have shown that the Donnan membrane potential, as given by cell 8, persists after a hole has been made in the membrane. This indicates that the Donnan membrane potential partakes of the nature of a diffusion potential enhanced by the very low mobility of the colloidal protein ions. Similar ideas were expressed by Murray. The concept of a membrane potential, like that of a diffusion potential, is unsatisfactory to theoretical physical chemists, because a single potential difference cannot be directly measured. It will be seen that cell A includes at least 3 phase boundaries which might be the seat of potential differences. Only if the membrane potential is defined as the observed electromotive force of a complete cell does the term acquire a definite physical significance. Such a definition is adequate for comparisons with bioelectric potentials because the latter can likewise only be obtained in terms of a measured electromotive force. Loeb's highest values for membrane potentials were obtained in the presence of only small amounts of acid or alkali, with no added salt. It is a property of the Donnan equilibrium that the unequal distribution of ions is repressed by the presence of any diffusible electrolyte at high concentration. Only if the concentration of the non-diffusible ions were very high could there be a Donnan effect of any great magnitude in saline solutions of physiological concentration. Loeb's hope that the Donnan membrane potential might serve to explain the origin of electric charges in living tissues has not yet been fulfilled. 9. Membrane potentials in systems not at equilibrium. Other models for bioelectric potentials have been constructed by Buettner, who has been CLSW. Kila include a Noye-Chikaz layer between two aqueous solutions. In such systems, there appear to be dissolved electrolytes in different parts of the non-aqueous layer, and the cell as a whole is not in equilibrium. These cells are remarkable because of the magnitude of the electromotive force, which unit d to 0.1 volt usumises, but Pluter value in explaining Einoth, or a type of cell in Y, equilibrium, years, to be abscempt uwehus 2 salt solutions, saturated by a dried colloidal nitrocellulose drand. Such a membrane is very different from the common dialyzing membranes. It is practically more permeable, at least in experiments not J-roll hanged for days or weeks, to water and to dissolved hydrolytes. It was shown by Michaelis, however, that there might be a slight exchange of cations, but not of anions between the two solutions, separated by such a membrane over a long period. Michaelis found for the CLLN electromoti E4 of the order of 50 MV. Jean-Lane disassatifusion potential of the sort given Aki approximate lie by actuation 10 modified by the fact that the mobility anion in the membrane was theoretically 0. If this were true, Ikekwachu 10 would take the form of equation 11, and the EMF would approach 58 to 57 MV. At 15 degrees, Flick dilute solution would be more positive because of the tendency of the cation to diffuse into it as far as electrostatic forces would permit, while the anion would be prevented from diffusing by the impermeability of tin rain. If Michaelis's calomel electrodes and salt bridges are RCI, laced by silver chloride electrodes, diffuse directly, Into the zero point 0.1 and 0.01 N solutions, the Elector G motive force is about 90 to 100 MV. USD out of the 54 NN observed when the membrane is pierced or entirely absent. Idicus seals are not in thermodynamic equilibrium, since the electromole of force is not zero when identical reversible electrodes are in contact with the two solutions. Of seal likes was found by Mihalis to be even higher when the solutions that saturated by the membrane were of different chemical nature, though of the same concentration. With 0.1 m hydrochloric acid and 0.1 m sodium chloride, he obtained an EMF of 140 MV. If this EMF were a diffusion potential, it would be given by equation 12, which may be written in the form if the mobility V of the anion is taken as 0 in the membrane, while the cations are awesome. To retain their ordinary mobilities, the excitation gives an EMF of only OOFI log giant 5 EOA 50. Instead of the observed 140, it was Luanfonoline DCML Lyle. The dry CFD Lodion may decrease fill the mobilities of some cations more than others. Even though it did not real, collodion membranes were also employed by Labes and Zane and Quebecki in the construction of interesting models, which could be polarized by the EESI direct current. These workers were able to imitate with their models some of the electrical behavior associated with electrotonus in muscle or nerve. Michaelis's Nuashurtilu EMF of C, old JX with higher CR concentrations of salt, the results were considerably less than the theoretical maximum given the absolute values of ionic concentrations or activities. But only of their ratios, further explanation was needed. An extension of the classical theories of Nernst, Emaek, and Donnan was Devil, ed independently by Tyrrell and L. Meyer and Sievers. These workers consider a charged membrane as having a fixed concentration or activity of immobile ions, whose charges are balanced by those of mobile ions. If the latter are not originally identical, W and phi ions in the solutions bathing the membrane, a rapid exchange of ions of light charge occurs. They assume that a local Donnan equilibrium prevails at each surfaces of the membrane, with the existence of two opposite Donnan membrane potentials, or Nernst E. Inside the membrane, there is assumed to be a linear concentration gradient of both ions of the electrolyte furnished by the external solute. The interior of the membrane is therefore the seat of a third indential difference, a diffusion potential whose value should be a proxy, mately given by a formula derived by P. Henderson, 1907. The whole membrane potential is set equal to the sum obtained by adding the Henderson diffusion potential to the difference between the two Donnan boundary potentials. The result is an equation which cannot be solved directly for either of the two unknowns, namely the hypothetical concentration of immobile ions constant of selectivity, and the ratio of ionic mobilities in the membrane. By assuming values for these quantities, Tyrrell showed that the formula would radiate variations in the membrane potential with concentration in the right direction to fit observed results. Meyer and Sievers worked out a graphical method of getting the unknown quantities from several measurements of the f-kilometer of cells containing a single salt, with fixed ratio of concentrations but very actual concentrations. Meyer and his co-workers used the selectivity constant as a means of characterizing membranes and prepared artificial membranes of various types. Some membranes gave EMF, values indicating that they were permeable only to cations, others to anions. Meyer has suggested that bioelectric phenomena may be due to the existence and morphological arrangement of membranes of both types in tissues, as well as to chemical reactions which produce or remove dissolved ions. Although this extended theory of membrane iotentials provides an explanation for some experimental facts, its GCN or validity is still not proven. On recalculating the data observed by Meyer in experiments with artificial membranes, Fetcher obtained a good many figures which he could not reconcile with the theory. 11 oxidation reduction potentials, The chemical reaction which takes place when current is drawn from any galvanic cell involves an oxidation and a reduction. In the reaction for cell I, hydrogen is oxidized to hydrogen ion at the hydrogen electrode, while ionic silver from silver chloride is reduced to metallic silver at the other electrode. When a cell operates spontaneously, the oxidation occurs at that electrode, which becomes the negative pole in the external circuit, while reduction occurs at the electrode, which becomes the J-oxidative pole. If a current is driven through the cell in the opposite direction from an external source, the direction of the cell reaction is reversed, and the opposite changes take place at the electrodes. By the use of arbitrary conventions, it is possible to express the standard potential, or for a whole cell as the sum of two standard potentials assigned to the individual electrode reactions. Lewis and Rudolf and other physical chemists have emphasized the value of the accurate determination of standard electrode potentials by means of cells without liquid junction. Tables of standard electrode potentials are familiar to all students of chemistry, and a very extensive tabulation of such data for inorganic systems has been made by Latimer. The term oxidation-reduction potential is generally used in a more restricted sense to denote the potential difference between a solution containing both the oxidized and reduced forms of the substance in question and an inert electrode, usually of platinum or gold. Here the substance of the electrode takes no chemical part in the cell reaction. It furnishes no ions to the solution, but merely takes up or gives off electrons. In the absence of a metal electrode bathed by a solution containing the oxidant Wm, Latimer, the oxidation states of the elements and their potentials and potentials, and reductant in question, there is no mechanism for the existence of an oxidation-reduction potential. Accordingly, bioelectric potentials cannot be oxidation-reduction potentials. It is possible, as was shown by Conant and Fieser, to obtain the value of the oxidation-reduction potential of an organic system from the electromotive force of a cell without liquid junction. A derivation of the equation for the EMF of such a cell has been presented elsewhere. This procedure has not come into general use, but most workers have employed cells of the type. If the EMF of this cell is added to the EMF observed for cell V containing the SAM buffer but no oxidant nor reductant, the sum is the EMF of a cell with negligible liquid junction potential. It is customary to express these potentials on the normal hydrogen electrode scale. This is accomplished by adding only the EMF which cell V would have if its solution had unit activity of hydrogen ions or 0 pH. That is the EO of cell V. The sum of this quantity and the observed EMF of cell X was designated by Clarke as E. It is related to the concentrations of oxidant and reductant by an equation first used by R. Peters, 1898. Peters' equation is for a system in which the chemical formulas of the oxidant and reductant differ only in their electric charge, and is here the difference between these charges in Faradays per mole or electrons per molecule. Strictly, the concentrations should be replaced by activities. When the oxidant and reductant are Phi and Fej, N is 1. For a large number of organic systems, such as that composed of quinone, C6H4O2, and hydroquinone, C6H40H2, the value of N is 2. The electrochemical reductant in this system is not hydroquinone itself, but its bivalent anion, CelHO. Hydroquinone is a very weak debasic acid. Accordingly, the law of mass action may be applied to both stages of its dissociation. The concentration of the anion may therefore be expressed in terms of the two dissociation constants, the concentration of hydrogen ions and the concentration of undissociated molecules of hydroquinone. If the hydrogen ion concentration is much larger than either of the dissociation constants, the total concentration of the reductant is practically identical with the concentration of undissociated molecules, and Peters' equation becomes DI. Hitchcock, Physical Chemistry for students of biology and medicine, Thomas for systems of this type E in not too alkaline solutions. The quantity IO high equation, 26, differs from the EO of equation, 25, because it includes the ionization constants of the reductant. The behavior of organic oxidation reduction systems is conveniently described in terms of values of AK at a specified pH and a 1:1 ratio of reductant to oxidant. If such values for different systems are known, it can be predicted that a system having a higher value under given circumstances will tend to oxidize a system of lower. The effect of the degree of oxidation on the A for a single system is represented by a sigmoid curve not unlike the dissociation curve of a weak electrolyte. For systems having the same value of N, the curves can be superimposed by shifting them along the axis. If N has different values for two systems, the curves will have different slopes. Examples may be found in the work of Clark and of McCallis. Oxidation reduction potentials of systems of biological importance have been considered in recent symposia. 1. Osmotic pressure. The direct measurement of osmotic J pressure requires a membrane which is perfectly semi-permeable, that is, one which allows the solvent to pass freely but holds back all dissolved substances. The membrane must also be sufficiently rigid to withstand the pressure, which may be very high. In the case of ordinary aqueous solutions of substances of low molecular weight, crystalloids, the existing data consist principally of those obtained with sugars by M.F.R.C. Fraser and collaborators, 1901-1923, and by Berkeley and Hartley, 1900 to 1916. Because of the difficulty attending such measurements, it is fortunate that the osmotic pressure may be accurately calculated from the ELU of any of the other colligativity properties, such as the freezing joint depression, as adjudicated in equations 46 to 48 of Chapter 3. The adequacy of such calculations, even for very concentrated solutions, is illustrated by the constancy of the ratios of the values of these two gyroptides for sucrose solutions. Table 111 gives experimental data for both properties at or near OGC, and the ratios in the last column are not far from the theoretical value, 12.06. Data from international oilical tape. The relation between osmotic pressure and concentration is usually found to show deviations from the logarithmic equation for ideal solutions, as well as from the linear equations of Morais and Van Hoff, Chapter 3, equations 42 to 44. These deviations may be expressed in terms of an empirical osmotic coefficient, G7, defined as the ratio of the observed to the ideal osmotic pressure. The exact value of G depends on the equation which is taken to represent ideal behavior. For solutions of physiological interest, the osmotic coefficient may be defined with sufficient accuracy by the relation in which Morse's equation is taken as the ideal law. The osmotic coefficient may also be obtained from the freezing point depression of an aqueous solution by the relation value of G for an aqueous solution of sucrose of any given concentration up to 4m. In these equations, xEm is the total mole concentration of all particles which are osmotically effective, that is, all molecules or ions. Osmotic coefficients for strong electrolytes are calculated on the assumption of 100% ionization. The values of the osmotic coefficient for a few typical salts and non-electrolytes, as calculated from freezing point data by equation 2, are plotted in figure 14. In each case, the value of PR is 1 at infinite dilution. If G were taken as 1 for a solution of glucose or urea having the same freezing point as mammalian blood serum, 0.56 degrees Celsius, the calculated concentration of such an isotonic solution would be an error by only 1 or U% if a similar assumption were made for salt solutions. The curves in figure 14 indicate that the calculated isotonic concentrations would be too low, by 7% in the case of Nasopol, 13% in the case of KCl2, and 45% in the case of NGS4. In general, it is true that deviations from the laws of dilute solutions increase markedly with the valence of ions. When only one solute is present, the osmotic coefficient is related to the activity coefficient and concentration of the solute by the differential equation if a set of values of G is known for corresponding values of C, may be calculated by the use of graphical integration. However, if either one or an is directly proportional to R, as in the Debye-Huckel limiting law, see below, the relation between a G reduces to the simple form. Equations 3 and 4 were first obtained by Bjerrum, 1916-1923. Their derivation is given in advanced textbooks if the solute is a non-electrolyte 1 or is generally proportional to 0. And in that case, the 3 in equation 4 is replaced by the factor 2, while the osmotic pressure of blood plasma or of a physiological saline solution is about 7.6 atmospheres at 38. It should be emphasized that an actual pressure of this magnitude is developed only when the solution is separated from the pure solvent by a perfectly semi-permeable and rigid membrane. This condition is never fulfilled in living organisms. Nevertheless, a knowledge of the magnitudes of osmotic pressures has served to explain many observations involving osmosis in biological systems, as in the classical experiments of De Vries, 1882, on plasmolysis, and of Hamburger, 1883, on hemolysis. Even if a membrane shows some permeability to dissolve substances, it is generally true that water passes through it more rapidly than most common solutes. Osmosis therefore occurs in that direction which tends to equalize the concentrations of water, even though dissolved substances may later penetrate the membrane. Negative and anomalous osmosis. It was observed many years ago, Dutrochet, 1835, Graham, 1854, that in certain cases there may be a temporary flow of water from a solution through a membrane into the pure solvent. Such negative osmosis was found when an aqueous solution of tartaric or oxalic acid was separated from pure water by a pig's bladder. It may also be demonstrated by an experiment described by Loeb if a permeable membrane of collodion nitrocellulose is soaked in a gelatin solution and washed with several changes of warm water, the membrane retains a coating or film of protein. If the membrane, in the form of a sac or test tube, is filled with water fitted with a stopper bearing a vertical H.S. Harnd in H.S. Taylor, ed., A Treatise on Physical Chemistry, Found Strand, New York, 1931, 2nd ed. D1, pages 780, EAA, Guggenheim, Modern Thermodynamics, by the Methods of Willard Gibbs, Methuen, London, 1933, P131 GN Lewis and M. Randall, Thermodynamics, and the Free Energy of Chemical Substances, McGraw-Hill, New York, 1923, pages 286, 842. The J of Lewis and Randall is identical with 1 GF as here defined. Selbach's Principles of Physical Chemistry glass tube, and submerged in a solution of phosphoric acid, water is found to rise in the tube for the first 20 or 30 minutes. In most cases of negative osmosis, the membrane has contained protein material and the solution has contained a fairly strong acid. Such experiments can be qualitatively explained as due to electroosmosis. It is known that an electromotive force applied across a protein membrane in contact with acid will cause water to move toward the positive pole. Although no external EMF is applied in the demonstration of negative osmosis, it may be assumed that a diffusion potential arising from the high mobility of the hydrogen ion has a similar effect. If the experiment is repeated with a collodion membrane not treated with protein, negative osmosis is not observed. In this case, the membrane does not acquire a positive charge in the presence of acid. Loeb also found negative osmosis when a gelatin-treated membrane was placed between a barium hydroxide solution and pure water. In this case, the alkali makes the protein negative with respect to the liquid, and the diffusion potential arising from the high mobility of the hydroxyl ion makes the water negative with respect to barium hydroxide solution. Negative osmosis has long been of interest to physiologists as a possible explanation of secretion, which involves the movement of water and ions against a gradient of pressure or concentration. If a permeable membrane, such as collodion, is placed between water and a solution of a non-electrolyte, sucrose, glucose, glycerol, etc., the direction of osmosis is normal. In such experiments, Loeb found that the increase in volume of the solution during the first 20 minutes was directly proportional to the initial concentration of the non-alketrolyte, even up to concentrations of 1 mm. This simple relation was found not to hold for many salts, particularly at low concentrations. While the osmosis was always positive, the increase in volume in a given time was greater at very low and high concentrations than in an intermediate region, where the curve of volume against initial concentration passed through a minimum. Similar results were obtained by Bartelf and others with membranes of various sorts. Apparently, the normal course of osmosis is opposed by electrical effects in a certain region of concentration. Since the results depend on the nature of the membrane and its possible electric charge, as well as on the nature and concentration of the salt, the complete explanation is rather involved. Reference may be made to the discussion by Greenberg et 3. Colloid osmotic pressure, although the total osmotic pressure of a physiological fluid is not readily obtained by direct measurement. The partial osmotic pressure due to colloid or very large molecules such as proteins can be measured without difficulty with the aid of a collagen or cellophane membrane. The colloid osmotic pressure of blood serum was first measured by Starling, 1896, and such measurements have been of D.M.A. Heinberg in C.L.A. Schmidt et al. The chemistry of the amino acids and proteins, Thomas Springfield, 1938, p. 814. See also R. Höber, chap 38 of this book. Great value in explaining the movement of fluid across the walls of capillary blood vessels. Apparatus and technique have been described by numerous workers, including Adair, Crow, and Nakazawa, and Sims. The colloid osmotic pressure of serum was discussed by Crouch and by Meyer. Measurements of the colloid osmotic pressure of solutions of purified proteins, Sprenson, 1917, Adair, 1904, yielded values for the molecular weights of egg albumin and hemoglobin, which were later confirmed by the use of the ultracentrifuge, Svedberg, 1926. In such measurements, the increase in osmotic gyroscope with the concentration of the protein is much more than linear. ID molecular weight is obtained by applying the Van Hoff equation to a value, extrapolated to zero concentration, of the ratio P, where P is the observed osmotic pressure, and C is the concentration in grams per 100 cc of solution. According to Adair and Robinson, a linear plot suitable for this extrapolation is obtained for some proteins by plotting PC against, while in other oses, it is preferable to plot CP against C. Similar methods of getting the molecular weights of proteins from osmotic pressure data were employed by Burke-4. Colloid osmotic pressure and membrane equilibrium. The partial osmotic pressure of an electrically neutral colloid may be measured directly without much error in the presence of any other dissolved substance, either ionized or non-ionized, to which the membrane is freely permeable. However, if the colloidal material bears an electric charge, as is often the case, the observed osmotic pressure will be due in part to the unequal distribution of diffusible ions characteristic of the Donan equilibrium. For example, we may suppose that a colloidal salt, nanar, is dissolved in water and placed inside a collodion sac. Let the sac be provided with a manometer and submerged in a sodium chloride solution free from colloidal ion. If osmotic equilibrium is attained, the colloidal solution must be under an excess of hydrostatic pressure, P. The value of P will depend not only on the concentration of the colloid, but on the difference between the concentrations of the diffusible ions, Ni and Chile. The concentration of each of these ions in the external solution at equilibrium may be represented by the same symbol, or if I represents the concentration of Ki alone in the colloidal solution at equilibrium, and Z represents the equivalent concentration of the colloidal anion. The condition of electroneutrality demands that the concentration of Na in the same solution be equal to Y plus Z. The distribution of ions at equilibrium will be as indicated in the accompanying diagram, in which the vertical line represents the membrane. According to Donan's theory of membrane equilibrium, the concentrations of diffusible ions at equilibrium must conform to the ion-Giroux equation 20, chapter 4, which may be written the total osmotic pressure of Koch solution may be calculated approximately. Equilibrium must be the difference between the total osmotic pressures of the two solutions, or the factor in parentheses is the algebraic sum of the molar concentrations of the ions. If Y is eliminated from equations 5 and 6, it follows that the total osmotic pressure of both ions of the colloidal salt should be times n plus 0. But equation 7 indicates that the measured pressure could attain this value only if x were 0, and if the ions of water played no part in the equilibrium. Equation 7 shows that the measured pressure would approach this value if Fortio and Sumer were much larger than if the solution also contained non-ionized colloidal material. Its molar concentration would have to be added to Zn in calculating the true colloid osmotic pressure. The part played by the Donan effect in the determination of colloid osmotic pressure will be illustrated by calculations which may have some bearing on the interpretation of measurements made with blood serum. The concentration of the proteins in serum is about 75 grams per 1,000 g water, and the protein is believed to exist as anions, whose charges are balanced by about 0.0. Principally, sodium ions colloid osmotic pressure of serum is determined largely by the albumin fraction. Its molecular weight is about 70, while that of the globulins is much greater. Adair and Robinson. We may therefore consider a hypothetical model consisting of an aqueous solution of a colloidal sodium salt having a molar concentration of 0.001 with respect to the colloidal ion, but 0.017 with respect to Na+. The value of Z is therefore 0.017, while that of Zn is 0.001. Samples of this solution are to be equilibrated across the membrane, permeable to salt and water, but impermeable to the colloidal ions against a series of solutions of sodium chloride. If the system is kept at 38 degrees, equation 7 indicates that osmotic equilibrium will be attained when the colloidal solution is under the excess pressures P, indicated in 28.3 mmHg, is in reasonable agreement with observed results for blood serum. The osmotic pressure due to the colloidal ion alone RTZFN is 19.4 millimeters. If Zn is 0.001, the last column of the table gives the differences between the values of P and this figure. That is, the last column represents the pressure due to the Doan-I effect. Unless the salt concentration is very high, this pressure is a considerable fraction of the total when colloid osmotic pressure is applied in the explanation of physiological phenomena. It is the whole effective pressure, P, that is wanted. On the other hand, if the results of such measurements are to be used to calculate the molecular weight of a colloidal electrolyte, the Donan pressure must be subtracted from P to obtain the pressure due to the colloidal material alone, which is RTZN-4 calculated values for the effective osmotic pressures at 38 of a colloidal sodium salt NiTr, 0.001 m. Against sodium locate solutions, the theory of membrane equilibrium and its application to systems containing colloidal electrolytes have been discussed by Donan, Loeb, and others, D. Emmer, and C. L. Avert. Schmidt, A. The Chemistry of the Amino Acids and Proteins, Thomas Springfield, 1938, Chapter 14.5. Amphoteric behavior of protein. As a result of electrochemical and physicochemical measurements made by Hardy, Osborne, Robertson, McAuliffe, Loeb, and others, the amphoteric nature of proteins was established. These substances bind hydrogen ions as CASC wiring positive charges when they aren't placed in acid solutions, and they appear to bind hydroxyl ions, acquiring negative charges, when placed in alkaline solutions. Since protein particles in solution are of colloidal dimensions, some have regarded this binding of ions as due to adsorption on the surfaces of particles. Most workers now consider that the charges of colloidal protein ions are best ascribed to chemical combination of Heilrod and ions with basic groups in the protein molecule, or removal of hydrogen ions by an ionization process from acidic groups. Evidence for the belief that proteins are amphoteric electrolytes was discussed elsewhere, and the amphoteric properties of certain proteins were considered in detail from this viewpoint at a symposium. The ionization of a protein or an amino acid in solutions of varied acidity or alkalinity is best described in terms of the ideas of Bronsted and Jerram concerning acids, bases, and ampholytes. If an amphoteric substance is placed in a solution containing also a strong acid in sufficiently high concentration, the ampholyte binds hydrogen ions to form a cation of maximal positive charge. If the solution is titrated with successive increments of a strong alkali, this cation behaves as a polybasic acid, losing hydrogen ions in successive stages. If the ampholyte is an amino acid, the successive stages of the titration and ionization may be revealed by breaks in the titration curve, and each step in the curve often resembles the typical titration curve of a single weak acid. In that case, the negative logarithm of an acidic dissociation constant, or pKi, is practically equal to the pH value of the solution at the midpoint of a section of the curve. In the case of a protein, the number of steps in the curve is much less than the number of ionizable groups known to exist in the molecule. But this is readily explained by analogy with the titration curves of peptides. On the assumption that the steps in the curve are masked or overlap when several groups have closely similar dissociation constants. The first part of the titration, from about pH 1 to 4, is ascribed to the removal of hydrogen ions from carboxyl groups. A buffering effect between pH 5 and 7 may be due to the removal of hydrogen ions, which were attached to the basic amino group of histidine. The latter part of the titration, from pH 8 or 9 to 12 or above, is thought to consist in the removal of hydrogen ions, which were combined with amino or gonadin groups. In this way, it has proved possible to reproduce the whole Turei-Ratio curve of an amino acid, peptide, or protein acidic ionization constants. The belief that these definite kinds of groups are titrated in the regions of pH, which have been indicated, was founded in the first instance on the probable magnitude of their JK values, as inferred from comparisons with those of similar groups in known amphoteric substances. Additional support was found in comparisons of the temperature coefficients of JK values, or of the heats of ionization derived from these coefficients. JT followed from this assignment of groups to pH regions that an amino acid or protein at its isoelectric point should exist, not as an uncharged molecule, but as a d-aolar or multipolar ion isotirion, carrying ECPL numbers of positive and negative charges. Live validity of this inference has been supported by studies of solubility dielectric constant and the Raman effect. It should be pointed out, however, that while the natural amino acids and proteins are believed to exist largely in the zwitterion form at their isoelectric points, this is not true of all amphoteric substances. Since ortho and para-arenino benzoic acids appear to exist chiefly as undissociated molecules. Many proteins and some amino acids exhibit minimal solubility at pH values at or near their isoelectric points, and this phenomenon has sometimes been used as a means of locating the position of the isoelectric point. Since the term isoelectric implies the absence of any excess of positive or negative charge, an isoelectric point is preferably determined by electrokinetic measurements. Other properties of proteins which show minima at or near the isoelectric point include osmotic pressure, viscosity, and swelling, while the membrane oxygenii changes its sign at the isoelectric point. The variations in these properties over a wide range of 7H values and electrolyte concentrations were explained by Loop's theory of colloidal behavior, which was based on the Donnan theory of membrane equilibrium and on the treatment of proteins as amphoteric electrolytes. An inspection of tables of isoelectric points indicates that most proteins are negatively charged at the pH values of physiological fluids other than gastric juice. 6. Electrokinetic phenomena. This term includes electrophoresis or cataphoresis, electroosmosis, streaming potentials, and sedimentation potentials. The last of these phenomena may be regarded as the converse of the first, while the third is the converse of the second. In each case, there are two quantities which may be measured directly, namely eye motion of one phase of matter with reference to another, and a potential difference which is applied to or produced by the system in question. The electrokinetic phenomena are explained by assuming that an additional potential difference, the electrokinetic potential or zeta potential, exists between the moving and stationary phases. The theory of electrokinetic phenomena was first worked out by Helmholtz, 1879. It was further developed by later workers. Discussions of the theory FRI to be found in electrophoresis usually refers to the motion of particles through a liquid under the influence of an electric field. The electric field is provided by an external source of potential connected with two electrodes, usually of a reversible type, dipping either into the exi-Erlenyental liquid or into other solutions in contact with it. The particles may be ions in true solution, colloidal ions like those of a protein's suspensoid particles such as colloidal gold or platinum, or relatively large particles such as gas bubbles, fat droplets, microscopic crystals, or other particles of suspended solids. Electrophoresis has been observed with bacteria, erythrocytes, and other biological cells. The velocities of ions in true solution were first obtained by the transference method, Elatorf 1853, which has also been applied to the study of proteins, Greenberg and Schmidt, 1924. Ionic velocities were obtained more directly by the moving boundary method, Lodge, 1886. This method, as improved by later workers, especially Makelinge and his collaborators, has yielded extremely accurate values. The moving boundary method was also applied to colloids, Burton, 1906, and was later developed, Tiselius, 1937, into a precise method for the investigation of proteins. Since the Tiselius apparatus may be used to test the homogeneity of a preparation or to separate it into definite fractions, as well as to measure mobilities, it has rapidly become a valuable tool in biochemical investigations. The electrophoresis of larger particles may be observed directly under the microscope. The microscopic method, Alice 1912, in improved form, has been used especially by Abramson. This worker was able to show that the mobilities of foreign particles which had been bathed in a protein solution were independent of the size, shape, or chemical nature of the particles themselves. Lai also found that the curve of mobility as a function of pH could usually be superimposed upon the titration curve of the protein. The microscopic method is more rapid and convenient than the moving boundary method, but a good many measurements are usually averaged before a reliable result is obtained when the microscopic method is applied to protein-coated particles. It must be recognized that the observed mobility is a property of the protein as it exists in an adsorbed film, and that the result may not always be identical with the mobility of the protein ions in a colloidal solution, free from foreign particles. Electroosmosis is the passage of a liquid through a diaphragm, membrane, capillary tube, etc., due to an electric field. An external potential difference is impressed upon two electrodes in contact with the liquid on opposite sides of the diaphragm, and the motion of the liquid as a whole through the diaphragm may be followed by observing a meniscus in a horizontal capillary tube, just as the isoelectric point of amphoteric particles is determined in terms of a solution in which the velocity of electrophoresis is zero. So the isoelectric point of a membrane may be obtained by finding a liquid of such composition that there is no electroosmosis. Both electrohoresis and electroosmosis seem to be involved in the introduction of drugs through the human skin by means of an electric current, Abramson, Moyer, and Gorin. This process has sometimes been called ionophoresis. Measurements of electrophoresis or electroosmosis are usually expressed in terms of mobility, that is, velocity per unit potential gradient, c introsec per volt centimeter, according to classical theory, Helmholtz or Lukowski. Perrin. The mobility should, in either case, be given by the equation here. F is the electrokinetic potential 1, is the dielectric constant of the liquid medium, and 77 is its viscosity coefficient. The factor 47R was obtained since the zeta potential cannot be measured directly. It was formerly customary to calculate its value from the measured mobility by means of this equation. More recently, it was pointed out, Debye and Hickel 1904, that for small spherical particles in an insulating medium, the factor 4T should be replaced by GTT. If the thickness of the double layer is much less than the radius of curvature of the surface, the classical equation is still believed to be valid for particles of any shape. Helmholtz treated the zeta potential as if it existed only between opposite charges in a thin double layer. Modern W-workers prefer the idea of Guy, 1910, who conceived of the charges in the liquid as dispersed through a diffuse layer or ion atmosphere. The potential difference responsible for electrokinetic phenomena is not necessarily identical with a potential difference of the sort postulated by Nernst 1889, as existing between an electrode and the solution bathing it. Some writers refer to these Nernst potentials as thermodynamic or epsilon potentials. Freundliche AG and Rona. 19.0 compared the potential difference across a thin glass membrane with that deduced from measurements of the streaming potential produced in tubes of the same kind of glass. The former depended almost solely on hydrogen ion concentration, while the latter was markedly influenced by minute concentrations of aluminum chloride or crystal violet. To explain such results, it is assumed that electrokinetic behavior depends only on a portion of the total potential difference, namely, on that existing between the fixed and movable portions of the liquid. A full understanding of the present state of electrokinetic theory is possible only for those trained in mathematical physics. Recent important progress has resulted from the application of improved electrokinetic technique, Tiselius, 1937, to materials of biological interest. This progress has depended on the accurate measurement of mobilities and has not involved the calculation of zeta potentials. Electrophoresis has been employed more often than electroosmosis, while streaming potentials and sedimentation potentials have received little attention. 7 dielectric, constant, and dipole moment. According to Coulomb's law of electrostatics, the force exerted between two electric charges is proportional to the product of the charges' amounts of electricity and inversely proportional to the distance between the charges. Faraday showed that the force depends on the nature of the medium which separates the charges, and accordingly, the constant of proportionality in Coulomb's law is different for different media. The dielectric constant is the reciprocal of this proportionality constant, so that the force between two charges tends to be low if they are separated by a medium of high dielectric constant. This is the basis of Ply-Nernst-Thompson rule, 1893, according to which the ionizing power of different solvents varies with their dielectric constants. Since ionization in solution often depends on the chemical properties of the solvent, for example, the affinity of water for protons, the rule is often inexact. The dielectric constant is always relative to that of a vacuum, which is taken as 1, and practically that of air is also 1. The dielectric constant of water is about 80, a value which is much higher than those for other common liquids, alcohol 25, ether 4, benzene 2. The dielectric constant is equal to the quotient obtained by dividing the electrical capacity of a condenser with its plates separated by the medium in question by the capacity of the same condenser with only air or a vacuum between the plates. Methods of measurement, as well as the interpretation of Ta2, the dipole moment of a molecule, in which two equal and opposite electric charges are separated by a definite distance, is equal to the product of D.A. McKinn's Principles of Electrochemistry, Reinhold, New York, 1939. The distance and the magnitude of one of the charges. A molecule may have a permanent electric moment, or it may have a moment induced by an applied electric field. Dipole moments are obtained by calculation, phi-OM measurements of dielectric constant, but the relation between the two quantities is not always a simple one. Theoretical and experimental work in this field has been summarized in monographs, and there is also much important work in current journals. Dielectric measurements indicate that water is a dipole, while carbon dioxide is not. It is inferred that the atoms in Ko2 arc, arranged symmetrically along a line, while the hydrogen atoms in H2O make an angle of less than 180 degrees with the oxygen atom. Symmetrical molecules such as methane and carbon tetrachloride are not dipoles, and benzene likewise has no dipole moment. A zwitterion is obviously a dipole, and the assignment of this structure to isoelectric amino acids, peptides, and proteins rests on the fact that their aqueous solutions have dielectric constants higher than that of water. The dipolar structure of these substances has been studied as specially by Cohn. She mentions that urea and the phospholipids also increase the dielectric constant of water. While fats have low dielectric constants, the dielectric constants of different tissues may thus be expected to vary widely, depending upon the electrical properties of the molecular components. 8. In Lurionic attraction theory. Although it has not been possible to measure the dielectric constant of any solution containing electrolytes in appreciable concentration, the dielectric constant of the solvent is a factor in the enterionic attraction theory of Debye and Hickel, 1923. One result of this theory is a simple equation relating the activity coefficient of an electrolyte to the ionic concentration of the solution. Here is the activity coefficient of an electrolyte whose ions have the valences Z and 22. G is a theoretical constant, and Dx is the ionic strength, defined in terms of the concentrations of all ions in the solution. The value of it depends on the dielectric constant of the solvent and the temperature. For aqueous solutions, it is 0.503 at 18 degrees, 0.5 degrees, and 0.522 at 38 degrees. The ionic strength, Z, may be defined as 0.5s, junges, or half of the sum of all the terms obtained by multiplying the molar concentration of each ion by the square of its own valence. Lewis and Landau originally defined X in terms of the molalities of the ions, but the Debye-Hickel theory uses concentrations. The ionic strength is quite different from the chemical potential of Gibbs, although the same symbol is commonly employed for either quantity. Equation 8 is a limiting law, which should be valid only if certain terms may be neglected, because the ionic strength is low. The activity coefficients of strong electrolytes are correctly given by this equation if G is of the order of 0.01 or less. For higher ionic strengths of the order of 0.1, the equation is sometimes useful. The value of B depends on the specific nature of the electrolyte and must be determined from the data themselves. The theory has yielded more elaborate equations for wider ranges of concentration, but these also contain empirical constants. The importance of the Debye-Hickel theory lies in the fact that it provided the first satisfactory theoretical interpretation of the variations from unity activity coefficients and conductance ratios of strong electrolytes, which are believed to become completely ionized. A full discussion of the theory and its application to weak as well as strong electrolytes is to be found in the book by Macklins. According to the phase rule, Gibbs 1875 to 1876, a system of R coexistent phases, each of which has the same and independently variable components, is capable of NF2R variations of phase if this rule is applied to the equilibrium between a gas and a pure liquid in which the gas dissolves, c.g. oxygen and water. The number of components is 2. At ordinary temperatures, there will be two phases, a liquid and a gas. Accordingly, the phase rule allows two variations or degrees of freedom. That is, if the temperature and pressure are both fixed, the composition of the system at equilibrium is also fixed. It follows that the solubility of a gas in a liquid must depend on the temperature and on the pressure. The nature of this dependence becomes evident if we treat the dissolving process as a reversible physical-chemical reaction. If it is found that heat is evolved when the gas dissolves, for the reaction is negative, and equation 89, Chappie 8, indicates that the equilibrium constant must decrease as the temperature is increased. In other words, such a gas will be less soluble at higher temperatures. This is generally true for most gases. In the few cases in which the opposite effect is observed, it is also found that heat is absorbed during the process of solution. If the equilibrium constant for the solution process is expressed in terms of concentrations, it becomes identical with the Ostwald solubility coefficient P. This coefficient may be defined by the equation in which C2 is the concentration of the dissolved gas and Ci is the concentration of gas in the gaseous phase in equilibrium with the liquid. Evidently, 8 will be constant if the mass law is valid in terms of concentration. This will be true if neither Ci nor C2 is very high. If the gas follows the perfect gas law, Ci will be proportional to the partial pressure of the gas. In that case, if is constant equation 10 is equivalent to Henry's law, which may be written in the form, although Henry's law, as is indicated by this derivation, is a limiting law for ideal dilute systems. It is found to fit the facts in many cases of practical importance. At ordinary temperatures and pressures, the solubilities of gases are often expressed in terms of the Bunsen absorption coefficient, A, which may be ELC-fined by the equation here V is the volume of solvent which contains, when in equilibrium with a gas of partial pressure P, an amount of dissolved gas which would occupy the volume under standard conditions, 0 degrees Celsius, and 1 atmosphere partial pressure, Po is this standard pressure. If equation 10 is combined with the definition of concentration ECNV, and the perfect gas law EPV equals nor EPV equals nor, it follows that is the Ostwald solubility coefficient may be obtained by multiplying the Bunsen absorption coefficient by the absolute temperature of the system and dividing by 273. In physiological work, the solubility of a gas is often expressed in volumes %. This refers to the volume which would be occupied under standard conditions by the amount of gas dissolved in 100 volumes of solvent under the experimental conditions. The solubility in volumes % is given by the following relations. Data on the solubilities of gases may be found in well-known reference books. The distribution of a dissolved substance between two immiscible liquids may also be treated according to the law of mass action. For the reversible physicochemical reaction, the equilibrium quotient is if the active masses are proportional to the concentrations. The distribution coefficient, Berthelot 1872, Nernst 1891, is a ratio of concentrations of the dissolved substance in the two liquid gases at equilibrium. The value of K is independent of the concentration in either phase only if the activity coefficients of the dissolved substance in the two phases remain in a constant ratio. If this were true up to the limit of saturation, the value of K would be simply the ratio of the solubilities of the solute in the two pure liquids. Variations in K are to be expected if the presence of varying amounts of solute alters the mutual solubility of the two liquids in one another, and if the solute undergoes partial dissociation or association in one or both of the liquids. In the latter case, the distribution coefficient for a single molecular species may be constant, but the actual stoichiometric distribution ratio will depend on the variable degrees of dissociation or association. These may be calculated if the proper equilibrium constants are known. Even in such cases, an approximate simple relation is often valid over a limited range. For example, benzoic acid in water is electrolytically dissociated, but the degree of dissociation is small, so that most of the acid in the aqueous phase exists as single undissociated molecule. Benzoic acid in benzene is not ionized, but forms associated molecules of twice the ordinary molecular weight. If it is assumed that this association in benzene is practically complete, while the dissociation in water is negligibly small, the mass law gives the expression which has been approximately verified by experiment. In general, if a substance exists largely as single molecules A in phase 1 and as molecules of a definite polymer in phase 2, the distribution law assumes the form this equation may be put into a form which bears a superficial resemblance to the empirical adsorption isotherm of Freundlich. Attempts to deduce the latter equation from the distribution law have not been satisfactory. for one would have to make improbable assumptions, either that single molecules exist in the solution and fractional molecules in the adsorb phase, or that only multiple molecules exist in the solution and single molecules in the adsorbed phase. Since Freundlich's equation does not apply in all cases of adsorption, it is best regarded as an empirical interpolation formula useful within certain limits. More complicated forms of the distribution law are given in advanced textbooks, and the values of many distribution coefficients are given in tables. The influence of one solute on the solubility of another is well known. For example, sodium chloride may be recrystallized by passing hydrogen chloride gas into its saturated aqueous solution, while alcohol or acetone may be salted out of an aqueous solution by the addition of a salt, which is very soluble in water. Carbon dioxide is much less soluble in a strong calcium chloride solution than in water, and even a non-electrolyte may decrease the solubility of a gas in water. There are also salting EG effects, as in the solution of a globulin in a dilute saline solution, and the increased solubility of silver chloride in concentrated potassium chloride solutions. Some of these solubility effects have been satisfactorily explained. For example, the de Biheckel theory was verified by studies of the solubility of difficultly soluble electrolytes in salt solutions, B. Bienstedt and Lammer, 1924. A general theoretical treatment of solubility, especially in systems composed, L. A. Schmidt, ed. The Chemistry of the Amino Acids and Proteins, Thomas Springfield International Critical Tables, McGraw-Hill, New York, 1928, also through P418. See also